One star in our sky is already dead by every law we know, yet it still shines, as if time inside it refuses to end. On nights when the air is clear, the sky feels like an obedient map, every star in its place, every light following rules older than memory itself. We trust those rules. They are the framework of stellar life and stellar death. Yet, a few stars defy that order so quietly that the universe almost hides their disobedience. They shine long after they should have fallen silent. They outlive their equations. One of them hangs above us even now, a soft point of light carrying a contradiction at its core. According to physics, it should have collapsed ages ago. Its iron core should have folded into a dense, catastrophic implosion. Its outer layers should have burst outward in a supernova grand enough to mark entire galaxies with its ghost. Instead, the star remains calm, steady, almost indifferent to its overdue death. Observatories Gaia, Chandra, Nicer, and the Very Large Telescope have all recorded the same quiet anomaly. Each instrument measures a different part of the star's behavior, and each one whispers the same conclusion. The star should not be alive. Its mass, its age, its internal structure all point toward a fate that has not yet arrived. A faint delay threads through its light, not a glitch, not noise, a soft hesitation, as if the star is pulsing through syrup instead of vacuum, as if something beneath its surface is running slower than the universe around it. To understand why this is so unsettling, imagine the inside of a massive star as a harmony of clocks. The outer layers keep time through pressure waves. The mid-layers keep time through turbulence and heat. But the core, the dense, iron-loaded center, keeps time through the curvature of space-time itself. Ordinarily, these clocks remain synchronized. Their agreement is what allows stellar evolution to follow predictable steps. But in certain dying stars, those clocks drift out of sync. Deep within, collapse may already have begun. Gravity may already be pulling the core inward, but the outer layers remain unaware, unchanged, serene. If collapse cannot spread outward, if the message cannot travel through the star, then the star remains alive from the outside's point of view. A kind of cosmic illusion, and here is the quiet break in our understanding. The moment that turns the entire phenomenon on its head. The star may already be collapsing inside, but the surface has not yet been told. For some reason, the signal of its death cannot reach the world beyond the core. The timeline deep within the star has slipped away from the timeline at its surface. A mismatch, a fracture, a disagreement between clocks that should never disagree. And in that soft fracture, the star survives. If you're still drifting with this mystery tonight, and you feel kind enough to support this quiet channel, leave a like, share the calm, and subscribe so the next whisper can find you. Now, let us go deeper. The idea that collapse has begun but cannot spread leads to a profound possibility. Time inside the star is flowing differently from time outside it. This does not violate physics. It stands on one of Einstein's most elegant truths. Gravity slows time. Where gravity intensifies, moments stretch, seconds lengthen, processes slow. In the extreme density of a collapsing core, even before a neutron star forms, time can already be warped. If the core's time slows dramatically, collapse may unfold over a few minutes internally, yet appear as tens of thousands of years to distant observers. The exterior of the star would look unchanged, undisturbed, still radiant. But even gravitational dilation alone cannot explain the full hesitation we see. Some astrophysicists suspect a deeper mechanism. Temporal shear regions inside the star, where the flow of time twists and drags because of magnetic turbulence, density gradients, and intense neutrino flux. These conditions could create internal pockets where time flows at mismatched speeds, like layers of a river sliding past each other, never fully blending, never fully agreeing. If collapse must pass through these fragmented pockets of time, it may lose coherence. The signal becomes distorted, slowed, refracted. By the time it travels outward, The upper layers have lived through far fewer moments than the core. In their timeline, collapse simply has not happened yet. And so the star continues to shine. This brings us to the thesis that will guide our entire exploration. A star does not end when physics says it should. It ends when time inside it agrees. The more astronomers observe these delayed collapse stars, the more the paradox deepens. Neutrino detectors record bursts that resemble the first signs of collapse, but they do not grow stronger. Surface imaging reveals convection patterns that lag behind theoretical predictions. The star's brightness carries a rhythm that seems to hesitate. A faint delay, always a faint delay. It is as if the universe has pressed the pause button on the star's collapse, not by choice, but by architecture. What does that mean? It means the star is not stable. It is suspended. Imagine standing beside a bell that has already been struck, yet you hear nothing. The vibration exists, but time has slowed the ringing so drastically that the air cannot carry the sound. The star may be in that same state, already collapsing, but its timeline stretched so far that the universe has not yet been reached by the echo. And this leads to the philosophical shadow of the scientific problem. If time can fracture inside a star, what else in the universe might be experiencing fractured time without our notice? The outer layers of a delayed collapse star glow peacefully, as if unaware of the catastrophe quietly unfolding within. But they are not resisting collapse. They simply have not arrived at the same moment. They are living in a different part of time. The implications of this are staggering. It suggests that stellar death is not a singular event, but a negotiation between misaligned timelines. It means a supernova is not born from a single instant of collapse, but from a moment when all the star's internal clocks finally fall into agreement. Until then, the star survives, not because physics has failed, but because time has not aligned. So let this chapter end on a soft breath, a quiet step toward the next question. If a star can delay its ending by slipping out of sync with its own timeline, what exactly is happening to the clocks inside it? Close your eyes for a moment. We will open that question in the next whisper. The question waits quietly at the edge of our awareness. If a star can delay its own ending, then what exactly is happening to the clocks inside it? When we think of time, we imagine it as a single, smooth flow, steady, impartial, flowing through every place in the universe with the same invisible rhythm. But inside a star, that rhythm becomes something else entirely. Time bends, time stretches, time thickens in pockets of gravity so intense that even light must reconsider how quickly it can move. Yet despite these distortions, the star behaves as if everything inside it is synchronized. Its pulses, its tremors, its cycles of heat and brightness all follow patterns we can measure and predict. This illusion of unity is one of the great wonders of stellar physics. A star is not a single object, but a layered world where countless processes agree somehow on a shared timeline, until one day they do not. To understand how that agreement breaks, we must first understand how it forms. Inside, even the calmest star, chaos reigns. Nuclear reactions blur into waves of heat. Pressure surges form knots of turbulence. Magnetic fields twist into spirals that can snap and reform in the span of a heartbeat. Amid this storm, the star must maintain an equilibrium, not just of force, but of time. Each layer adapts to the signals from the layers around it. Each region carries the memory of millions of years of energy flowing outward, like the inheritance of an ancient clock. And yet, when astronomers describe this internal harmony, they use deceptively simple words: core, radiative zone, convective zone, photosphere. These terms evoke structure, but inside a star, structure is nothing like the still diagrams we draw. A star is not a calm onion of layered shells. It is a living turbulence, a sea of reactions in near constant dispute. But even seas have clocks. The first clock inside a star is pressure. Waves of compression ripple outward from the core, moving information through the stellar interior at incredible speed. These waves tell each layer how to respond, how to breathe, how to expand or contract. The star's heartbeat is carried through pressure. The second clock is temperature. Heat determines how fast particles collide, how quickly energy moves, how strongly the star can resist collapse. Temperature shifts create a rhythm that tells the star when to brighten, when to dim, when to churn more violently. The third clock is gravity itself, the most ancient clock of all. Gravity shapes time. It slows it. It drags it downward into wells carved by mass. The deeper the well, the slower time flows. The core of a massive star lives at the bottom of a well so deep that time there already runs more slowly than at its surface, even while the star is still healthy, long before collapse becomes possible. And the fourth clock, the one we understand least, is turbulence. Magnetic fields, rotational shear, convection currents, these processes create rotating pockets of motion that resist any single rhythm. They twist the flow of time just a little, dragging it into pockets where reactions lag behind their neighbors. For millions of years, these clocks remain close enough in sync that the star behaves as a unified object. But all stars age. All stars accumulate iron. And eventually, the clocks begin to drift. This drift is gradual at first, subtle enough to hide within the normal breathing of the star. Pressure waves slow. Heat redistributes unevenly. Turbulence deepens. And deep in the core, gravity's well grows so steep that time stretches further, thinning like a thread pulled too tight. If the star is small, the clocks remain close enough to trigger collapse at the right moment. If the star is massive and unlucky, something stranger happens. The core reaches the threshold of instability. Gravity takes control. Collapse begins. But the outer layers do not feel the change. They are still living in an earlier moment, a different part of time. Collapse is unfolding in a timeline the surface has not yet reached. This is the first true fracture. Astronomers studying these fractures describe them with caution. The language of physics is not built for describing mismatched timelines inside a single object. Yet the data reveal the unmistakable pattern. Neutrino emissions shift before surface brightness responds. Turbulence deep within accelerates while the surface remains serene. The spectral lines show subtle lags, as if the star is trying to speak through a delayed signal. This is the faint delay, again too soft to disturb the star's glow, but too persistent to ignore. The deeper question is this: why does the star not collapse anyway? Why does the core not force its timeline onto the layers above? The answer may lie in the structure of collapse itself. When a core begins to fall inward, it sends out pressure waves, shocks announcing the change. These shocks travel outward, carrying the message, the star must die now. But if the shock must pass through layers of time that are running at different speeds, the message becomes distorted. The shock weakens. Its timing changes. It may even break apart into smaller waves. By the time it reaches the surface, if it ever reaches it, the information is too faint, too stretched across mismatched moments to trigger the supernova. The star is collapsing, but only in a region of spacetime where collapse has already begun. To everyone outside, the star still appears whole. Some astrophysicists compare this to a bell being struck underwater. The vibration exists. The sound does not carry. The collapse exists. The timeline cannot transmit it. Other researchers propose that magnetic turbulence inside the star creates what they call temporal boundary layers, regions where time's flow is dragged sideways instead of forward, like a current caught behind a rock. Collapse trying to pass through such a layer would lose its coherence, dispersing like a broken wave. Whatever the mechanism, the result is the same. The clocks no longer agree. And here lies the philosophical heart of the problem. We assume events in the universe happen at specific times. We measure them, predict them, chart them. But a dying star reveals a more complex truth. An event does not truly happen until all the regions involved reach the moment together. Collapse requires consensus. A star does not end when physics says it should. It ends when all the clocks inside it arrive at the same conclusion. This reframes stellar death in a way that feels strangely human, less like an explosion, more like a gathering, a synchronizing of timelines. Every layer must catch up. Every pocket of slowed time must drift forward. Every delayed region must surrender to the final moment. Until that happens, the star continues. It shines through a death that has already begun. It endures across mismatched timelines. It holds together in defiant calm, carrying the slow pulse of collapsing light. For scientists, this creates a new challenge. How do you measure an event that is not simultaneous within its own object? How do you model a collapse that unfolds at different speeds in different layers? What defines the moment of death, if not the collapse itself? Theories multiply. Simulations contradict one another. Observations resist clarity. But somewhere beneath all this uncertainty lies the hidden truth of stellar endings. For now, let this thought drift with you. If the clocks inside a star can drift apart, what holds them together through most of its life? What ancient harmony keeps a star aligned until its final moments begin to slip? We will follow that question in the next whisper. Close your eyes. Feel the faint delay in your breathing. The universe is still letting the next moment arrive. Across the quiet dark between stars, there are places where explosions should have happened. Places where the sky should have torn open in light so bright it could have rewritten the night. These vanished supernovae are not myths, not approximations, but predictions rooted in models we trust more than almost anything in stellar physics. And yet, the explosions never came. Some of these stars were catalogued decades ago as imminent collapses. Some were marked centuries ago in ancient observations as unstable giants nearing their end. Others sit in galaxies so distant that their light left long before humanity learned to write numbers. But all of them share one impossible feature. They should be gone. Their cores should have reached the critical mass. Their reactions should have halted. Their gravity should have folded them inward until no force could resist. But the sky is still intact. It is quiet where it should be broken. Astronomers call them missing supernovae, though the name feels more like a placeholder than an explanation. The term grew from a simple expectation. Massive stars end violently. They do not fade gently. They do not linger. Their death is one of the most explosive events in the cosmos, releasing more energy in seconds than our sun will emit in its entire lifetime. But when researchers compared the number of predicted supernovae to the number we actually see, a strange emptiness appeared in the data. A gap, a silence. Whole categories of massive stars simply refuse to explode. This is not a matter of chance. It is a systematic absence. One of the earliest hints came from the observations of red supergiants, stars so swollen and unstable that they should be on the brink of collapse. They burn through their fuel layers at astonishing rates. They build their iron cores rapidly. They drift into the final threshold, like giants carrying their own gravestones. Yet many of them remain luminous, whole lists of them. Gaia's catalogs show giants whose age and mass estimates place them far beyond the expected collapse window. Their surfaces churn with convection cells that look ancient, tired. Their internal chemistry shows depleted elements that should signal an imminent end. And still, decade after decade, they shine. The Very Large Telescope has observed stars with iron signatures so strong that the models predict collapse within days. But the days turn into years. The years stretch into human generations. The star does not change. NICER records timing variations in soft X-ray emissions from blue supergiants, tiny oscillations that resemble the breathing of a star under immense internal stress. Those oscillations should escalate into full collapse as the core gives way. Instead, they stabilize, as if the star has decided to hold its breath forever. Chandra's X-ray data reveals density waves rippling through certain unstable stars, patterns identical to the opening motions of a collapsing core. But unlike the collapse we expect, the ripple does not tighten. It fades. It drifts. It becomes part of the star's ongoing rhythm. It is as though collapse begins, then pauses, begins again, then dissolves. A hesitation, a faint delay that keeps repeating. The more astronomers look, the clearer the pattern becomes. Some stars enter the early stages of collapse repeatedly, but never reach the event that ends them. This should be impossible. To understand why, imagine a towering building whose foundation has already cracked. Once the structure begins to fall, no force on Earth can reverse the motion. Collapse accelerates. The fall is inevitable. A star is even less forgiving. Once the iron core can no longer support itself, the collapse accelerates beyond any hope of stabilization. The process is not supposed to stall, but it does. In the most extreme cases, the models say the star should have died millions of years ago, and yet we see them today, shining with the worn-out glow of something that has overstayed its place in time. Why does this happen? The standard explanations fall apart quickly. Measurement error? The values are confirmed across multiple observatories. Incorrect models? The physics of core collapse is one of the most thoroughly tested phenomena in astrophysics. Hidden companions or mass transfer? Possible in some cases, but not across entire populations. So the question grows heavier. What prevents a star from dying when all conditions say it must? Hints emerge again from neutrino data. Neutrinos are the earliest messengers of collapse. They fly outward long before light can escape. In some of these stars, neutrino detectors catch subtle, sporadic bursts not strong enough to signal collapse, but too patterned to ignore. It is as if the core is trying to signal its failure, but the message disperses, echoing through a maze where time flows unevenly. Surface temperature fluctuations also whisper clues. Some giants show cooling cycles that match the expected final stages of stellar evolution, except the cycles repeat. They loop. Instead of falling into the steep decline that triggers collapse, the temperatures wander and drift, as if the transitions are being stretched across mismatched timelines. A star can only behave this way if collapse is no longer a single moment, but an extended argument inside itself. This leads to the unsettling interpretation that is beginning to take root in theoretical astrophysics. The timeline of collapse is starting in the core, but it cannot reach the rest of the star. The outer layers are still living in an earlier moment. The inner layers have already crossed into the next. The star is divided across time. The forgotten supernovae are not missing because they never formed the conditions for collapse. They are missing because collapse cannot synchronize across the star's internal clocks. The star is trying to die, but different regions disagree about when the death is happening. Some parts have arrived at the final moment. Other parts have not yet lived through the moments leading to it, and until every region reaches the same moment, the star endures. Light from these stars reinforces the idea. Spectral lines shift in patterns that suggest internal turbulence out of alignment with surface motion. It is like watching a dancer whose movements no longer match the music. Something out of sync, something delayed. A faint delay, always the same faint delay. This phenomenon challenges everything we assume about how the universe records events. A supernova is supposed to happen at a time. But if a star is trapped in mismatched timelines, then the time of collapse is not a single moment. It is a region, a stretch, a negotiation, a place where time itself must converge before the star can fall. The forgotten supernovae, then, are not forgotten at all. They are not lost or absent. They are still unfolding, deep inside, just in a timeline the surface has not yet reached. This raises a question that casts a long shadow across the chapters to come. If a star can begin its death without ever completing it, what does that say about the nature of endings themselves? We imagine endings as singular points, but the stars whisper a different truth. An ending is only real when every part of a being arrives there together. Let that settle for a moment. The universe is quieter than it used to be, because some of its explosions are still waiting for their clocks to align. And so this chapter drifts toward its final breath, with a soft invitation into the next. If collapse can begin without completing, then perhaps the real mystery lies not in why stars die, but in what keeps them alive long after the moment of death has already begun within them. We will follow that thread in the next whisper. Close your eyes, feel the faint delay between your heartbeat and your breath. The universe is still deciding when its moments agree. The forgotten supernovae leave us staring into a deeper tension, one that does not come from light curves or temperature drifts, but from something more intimate and more difficult to measure. Deep within these stalled giants, there seems to be a pressure resisting collapse. Not thermal pressure, not electron degeneracy, not neutrino trapping. Something else, something the equations do not name. To understand why this matters, imagine standing inside the core of a dying star at the very moment when iron has filled the heart of its furnace. In every standard model, this is the instant when support vanishes. Fusion cannot continue. The star loses the force that once held it open. Gravity takes over without mercy. Every remaining moment should accelerate toward the end. But something inside these delayed collapse stars refuses to surrender. The signals of collapse flicker, rise, and then flatten out, as if some unseen resistance holds the core in suspension. Astronomers describe it as a false equilibrium. But the term is just a placeholder for our uncertainty. If thermal pressure were responsible, it would collapse with the core's temperature loss. If degeneracy pressure held the line, it would collapse as iron density rises. If neutrinos were trapped, their escape would break the balance within seconds. Yet the balance persists. Not entirely stable, not collapsing either. A limbo under impossible strain. Some researchers turn their attention to the movement of particles so deep inside the star that we can only infer their behavior indirectly. Neutrinos escaping in faint bursts, electrons crushed into tighter configurations, photons scattering through layers of turbulence that distort their paths. But none of these processes provide enough resistance to stall collapse for even a day, much less the centuries or millennia implied by observation. This is why the anomaly feels so heavy. The universe is showing us a kind of pressure that should not exist. One theoretical group proposed a new mechanism, a kind of temporal shear pressure. A force emerging not from particles, but from the disagreement of time itself. If the inner region of the star is collapsing in a slowed timeline, while the outer layers are still living through earlier moments, then the interface between these timelines becomes a boundary, a place where changes cannot pass cleanly. Think of it as a seam inside the star, where moments pull at each other. A region where the star resists collapse not because of force, but because the layers simply cannot coordinate the event together. Temporal shear is not a force in the traditional sense. It is not something that pushes or pulls. It is a byproduct of time, not flowing consistently. Where the flow stretches or compresses, processes that rely on synchronized timing lose coherence. Pressure waves cannot maintain their shape. Collapse signals cannot propagate with integrity. The star remains structurally stressed, but the failure cannot spread. This mismatch of internal time might be enough to create what looks like pressure from the outside, a holding shape that is not actually a force at all, but a symptom of two timelines refusing to align. We cannot measure this directly. No probe can enter a star's core. No instrument can measure the flow of time inside a region where space-time is being distorted by gravity, turbulence, and nuclear chaos. But we can see the symptoms. Gaia reveals surface oscillations that respond too slowly to internal changes. Chandra detects thermal transitions that stall at inconsistent rates. NICER shows timing jitter in X-ray pulses that is neither random nor periodic, a pattern that looks, in some sense, like interference between mismatched rhythms. What we observe is not stability. It is tension frozen in slow motion. Imagine a vast metal bridge under extreme weight. If the supports weaken at equal rates, the collapse is inevitable. But if parts of the bridge weaken in different timelines, if one beam enters failure minutes or hours before the others, then the structure may hold far longer than expected, not because it is strong, but because the failure has no coherent path to travel. A star may be experiencing the same fractured sequence. Inside, collapse may be cascading through a slowed moment, stretched thin by gravity. Outside, the star has not yet reached the instant when collapse should begin. The mismatched flow creates a region where collapse cannot propagate. And so the star holds, trembling in a silence too deep for light to reveal. The existence of this temporal boundary layer, if it exists, would challenge our understanding of time far beyond astrophysics. It suggests that in highly dynamic gravitational environments, time does not merely run slower or faster. It may fracture into domains, unable to maintain consistency across space. Within such a star, some regions might be experiencing collapse that lasts minutes, while others are experiencing minutes stretched into centuries. If the collapse event must pass through these regions to reach the surface, the event becomes diluted like a wave trying to pass through gelatin instead of air. The surface remains luminous. The core remains doomed. Both states are true. Neither state can complete itself. This duality may explain why some stars remain stable far past their predicted death. It also explains why the signs of instability never fully disappear. They echo, looping through mismatched temporal layers. And again, there is that motif of faint delay. It lingers in the star's brightness, in its temperature drift, in the slight irregularity of its spectral lines. A heartbeat out of phase with itself. Some scientists argue that such a temporal boundary is too exotic to be considered without direct evidence. Others note that we already accept time dilation, redshift, and gravitational curvature phenomena that once seemed impossible before being observed. If temporal shear is real, then collapse is not a singular event, but a negotiation between regions trying to agree on a shared moment. The question left hanging in the data is simple but enormous. If this resistance comes from mismatched time, how does the star ever complete its collapse? Does the inner region eventually accelerate into the same timeline as the outer layers? Do the outer layers drift toward the slowed moment inside? Does the boundary dissolve as pressure intensifies? Or does something else entirely force agreement? We do not know yet, but the next stage of the mystery begins before this thought even settles. Because if a star holds itself between collapse and endurance, then somewhere within that boundary is a signal we have not yet learned to read. A signal carried not by pressure or heat, but by time itself. And that signal is about to reveal a behavior stranger than resistance. A moment where even light appears to hesitate. There is a moment in the study of dying stars when attention shifts from mass, density, and gravity to something far more delicate, the behavior of light. For all the force and violence inside a massive star, its outer expression is quiet. It speaks through brightness, through color, through slight undulations and rhythm. And when those rhythms fall out of step with expectation, scientists notice light is usually the most obedient storyteller in the cosmos. It travels without weight, without memory, without hesitation. Once released, it carries the exact imprint of the layer it came from. Temperature, motion, turbulence translated into wavelengths we decode with careful instruments. A star may hide its deepest processes, but its light cannot lie. Except, perhaps, in the strange case of delayed collapse stars, where even light seems uncertain. For years, astronomers studying these objects assumed their brightness patterns were stable. Their luminosity curves looked calm, even serene, with only the usual noise produced by convection cells shifting across their surfaces. But as instruments grew more precise, especially under the measurements from missions like Kepler and TESS, something subtle appeared. A pause, a drag, a hesitation in the light itself. Not enough to disrupt the overall brightness, not random enough to dismiss, not strong enough to mark instability, only delayed. Just a faint delay, repeating at irregular but meaningful intervals. It showed up first in the star A.G. Carinae, a luminous blue variable known for dramatic fluctuations. But in one particular cycle, its brightness dipped slower than the thermal model predicted. The dip lingered. Then, when the luminosity rose again, it rose with a delay, like a breath held too long before release. At first, researchers blamed measurement noise or dust interference. But the same hesitation appeared in multiple observations. Then it appeared in unrelated stars, red supergiants, Wolf-Rayet stars, aging blue giants, objects that should not share luminosity behavior. The pattern was unmistakable. The light emerging from these stars was arriving through a distorted timeline. Brightness is supposed to be a direct reflection of surface processes. When convection shifts heat upward, luminosity responds quickly. When turbulent zones rearrange, the changes propagate with predictable timing. But here, the changes drifted. The rhythm of the surface no longer matched the rhythm of the interior layers feeding it. Something inside the star was slowing the transmission of information. Imagine a whisper passing through several rooms. In a normal star, the whisper travels cleanly from core to surface. carried by pressure waves and thermal flow. But inside a delayed collapsed star, the whisper moves through regions where time itself pulls at different speeds. By the time the light reaches the surface and escapes into space, it carries the shape of that struggle, slightly muted, slightly late. Brightness patterns from tests revealed faint plateaus where transitions should have been steep. Gaia detected microvariations in motion that suggested delayed reaction forces. The Very Large Telescope observed surface granulation shifting with a tempo that seemed out of sync with the star's pulsation frequency. Each dataset told the same quiet story. Light hesitates. If the core is collapsing in a slowed timeline and the outer layers do not yet share that moment, then the radiation emerging from intermediate zones must pass through mismatched layers of time. A photon born in a region where collapse has already begun may have to traverse zones where collapse has not yet arrived, zones whose internal clocks run faster or slower than the one where it originated. The photon's path stretches. Its release moment distorts. It is not slowed in space. It is slowed in time. This is not time dilation in the classical sense. Classical dilation affects everything uniformly at a given radius from the gravity source. But the irregular hesitation detected here suggests something else. Regions within the star, where the flow of time is not smoothly curved, but jagged, turbulent, layered, a sporadic stretching of moments. Some theorists have begun to refer to this as temporal viscosity, not a force, but a resistance arising when timelines cannot align. Light becomes a tracer for these internal disagreements. It moves through the star like a swimmer navigating currents that shift direction and thickness unpredictably. The faint delay becomes a map to deeper instability. Even when no explosion occurs, the luminosity tells us the core is reaching the critical point repeatedly. The surface ignores these signals for reasons we no longer attribute to force alone. The hesitation in the outgoing light is the signature of a star whose internal messages cannot unify into a single event. This raises an uncomfortable contradiction. If light carries the shape of the delay, does that mean the star's interior is collapsing in slow motion? Or does it mean the collapse is happening normally, but time itself is stretching around it? Both interpretations lead to profound consequences. If collapse is in slow motion, then the star may remain suspended for far longer than any model predicts, maintained not by pressure but by temporal mismatch. If time is stretching, then collapse may complete internally, yet never propagate outward, because the boundary between moments thickens faster than events can cross it. In either case, the star's death is no longer the sequence we understand. It is something fragmented. Light shows this most clearly during oscillation cycles. Normally, brightness responds to pulsation with near-synchronous timing. But in these stars, peaks arrive late. Valleys arrive late. Changes in wavelength arrive late. It is as though the star is pulsing on two different metronomes, one tied to the inner core, the other tied to the surface, and neither aware of the other's timing. This misalignment grows more pronounced the closer the star moves toward what should be collapse. The faint delay intensifies. It widens into moments large enough for instruments to catch with certainty. Yet the star itself remains deceptively calm. To an observer unaware of the underlying tension, the star seems healthy, bright, consistent, glorious. But the light carries the truth of a deeper unraveling. The hesitation is not merely brightness behavior, it is collapse trying to reach the surface, slowed into near stillness. Some astrophysicists suggest that if we can decode the precise timing of these hesitations, we might be able to reconstruct the interior time flow of the star. Each delay reveals a stretch in the timeline. Each lag marks a region where collapse has faltered. A full map of the delays could show us the architecture of temporal fracture itself. This idea has launched entire research programs. Models now attempt to simulate how light travels through uneven temporal regions, but the complexity is staggering. Collapsing cores produce intense gravitational gradients. Convection produces chaotic temperature fields. Magnetic shear twists space-time subtly. Neutrino outflow alters pressure. Every process interacts with time flow, and time flow alters every process. Yet the light reaching our instruments carries those interactions in its hesitation. The star gives us just enough to suspect, but not enough to know. This uncertainty forms the heart of the conflict. If we cannot trace the path of light precisely through the star, how can we define when the collapse begins or ends? If the delay widens beyond a threshold we cannot detect, could a star collapse internally without ever signaling its death? There are models, now highly speculative, but grounded in data that suggest entire collapses might occur in regions so temporally stretched that no supernova ever emerges. The star dies in a timeline the universe never enters. If such collapses exist, then our count of supernovae is not incomplete. Our definition of now is incomplete. The faint delay becomes not just a clue, but a symptom of an entirely different kind of ending, one that does not break the sky, does not flash, does not announce itself. And if light can hesitate, if it can falter in its path through time before reaching us, then perhaps the phenomenon is not limited to brightness alone. Other signals, neutrinos, gravitational ripples, turbulence, might also be caught in the same slow currents, stretched by the same disagreements, which leads to the next question that begins forming even before this one settles. If hesitation appears in the light escaping the star, what deeper hesitations might be hidden in the layers the light passed through, waiting to reveal themselves in ways we have not yet learned how to see? And as that question opens like a quiet corridor, it pulls us toward the next whisper, a place inside the star where resistance begins to take a shape of its own, long before collapse and long before light can carry its story outward. There comes a moment in the study of delayed collapse stars when the conversation shifts from the behavior of light to the deeper machinery shaping that behavior. Hesitation in luminosity suggests hesitation in structure, and hesitation in structure suggests hesitation in time. But how can a star, an object made of plasma, gravity, and fusion, develop something as intangible as inertia in the flow of its own time? To explore that question, astronomers turn back to the data not as isolated signals, but as echoes of an underlying rhythm. Surface oscillations, spectral delays, angular irregularities, neutrino bursts, convective drift, all of them shared a quiet commonality. A lag, a drag, a resistance to change that no classical force could explain. Some called this resistance anomalous equilibrium. Others called it metastability, under collapse. But one description began to hold more weight than the rest. Stellar temporal inertia, not a proven phenomenon, not a defined mechanism, just a hypothesis, growing roots everywhere the faint delay appeared. Temporal inertia, in its simplest form, is the idea that time inside the star carries momentum. Not literal momentum in the sense of mass or motion, but a persistence, an unwillingness to shift from one temporal state to another. If time within the star is moving at multiple speeds, then the transition between those layers may not be instantaneous. It may resist correction. It may hold the star in a shape that physics alone cannot account for. A star could be collapsing in one region and retaining form in another, because those regions have not yet agreed on a unified flow of moments. To understand how radical this idea is, imagine dropping an object into a pool of still water. The ripples move outward immediately. Nothing resists the spread of motion except viscosity. But inside a star, if time itself has viscosity, then collapse cannot spread like ripples. It would move through layers of differing temporal density. Thick moments, thin moments, stretched moments, each resisting alignment. The collapse signal slows. The surfaces remain unaware. The star persists between realities. This is what temporal inertia attempts to explain. It begins with gravity. Gravity bends space-time. And the deeper the well, the slower time flows. The core of a massive star, nearing collapse, becomes a well steep enough to distort moments significantly. But instead of forming a smooth gradient between core and surface, turbulence disrupts the curve, producing variations. Areas of intense magnetic shear may slow time unevenly, creating temporal pockets. Convection currents may stretch moments vertically, Standing waves may lock certain layers into rhythms slightly behind or ahead of their neighbors. These layers form zones, temporal domains, each carrying its own internal timing. Ordinarily, such domains would exchange information fast enough to stay synchronized. But collapse breaks that synchronization. Collapse accelerates the deep layers while slowing the outer one's response. The mismatch widens, the inertia grows, and the star enters a state where collapse begins but cannot continue. Temporal inertia does not push back the way pressure does. It does not support the star. It simply delays the star's ability to recognize its own collapse. It smears the event across multiple timelines that cannot reconcile the moment of failure. Inside the star, some regions are already in the after of collapse. Others are still living in the before. Between them lies the hesitation, subtle, persistent, soft as a breath. This hesitation shapes everything that reaches the surface: heat, pressure, turbulence, and especially the light we measure from Earth. A photon that emerges from a deeper temporal domain carries the memory of the delay woven into its wavelength. A pressure wave becomes distorted, losing coherence across the boundary. Even the star's oscillations feel elongated, as if the star is trying to shift weight between timelines but cannot settle. Some scientists resist the hypothesis entirely. If time can resist change, they argue, then time has become a medium, not a parameter. But the growing data does not easily fit into simpler explanations. A.G. Carnet's delayed luminosity, Betelgeuse's unusual dimming cycles, the stable instability of certain red supergiants, the missing supernovae that never appear. All of them show the same slow drift between expected signals and observed ones. Temporal inertia may not be the cause, but it describes the behavior better than any model so far. The concept becomes even more compelling when considering what happens near the Chandrasekhar limit. Once the core hits that threshold, the change should be instantaneous. But if the core is living in a region of slowed time, instantaneous becomes complicated. The outside layers wait for a signal that has already occurred but has not yet reached them. The core collapses silently. The surface holds its breath for an ending that does not arrive. This mismatched existence creates tension. The star is held together not by equilibrium, but by disagreement. The collapse and the endurance coexist. Light hesitates because collapse hesitates. Collapse hesitates because time hesitates. Temporal inertia becomes the invisible scaffolding around this suspended catastrophe. And yet, even this hypothesis leaves an unanswered question drifting at the edge of comprehension. If time inside the star is resisting alignment, what finally forces it to agree? Collapse is a convergence event. Everything must reach the same instant. But if the timelines refuse to synchronize, does the star ever reach that point? Can collapse remain trapped within the core indefinitely, repeating its attempt across stretched moments that never reach the surfaces now? Or does something break the stalemate? The models fracture in different directions. Some suggest the growing mass of the core eventually drags all timelines downward into a shared collapse. Others propose that turbulence dissolves temporal pockets over long scales. A few speculate that gravitational waves generated inside the core may carry enough curvature to unify the star's internal time flow. But none of these explanations account for the stars that seem to resist collapse for far longer than their expected lifetime. Stars we continue to observe today, glowing with the soft persistence of light that should not exist. Temporal inertia might answer how they resist. It does not answer what comes next. And as the question expands beyond theory into a deeper layer of the phenomenon, another thought begins to form, subtle and unresolved, pulling at the fabric of our understanding before we can even shape it fully. If time holds the collapse in place with its own inertia, what happens at the boundary where the collapsing timeline meets the timeline that refuses to collapse? Because somewhere in that boundary, something is happening that our instruments cannot yet resolve. A behavior stranger than hesitation, and more revealing than delay. A place where the star's interior meets a limit beyond pressure, beyond inertia, and the whisper of that boundary begins to rise before we are ready to hear it. The deeper we follow the delayed collapse inward, the more the star begins to feel like a world made of boundaries, some familiar, some invisible, and one boundary in particular that should not exist at all. It lies just beneath the iron core, in a region where gravity grows sharp enough to bend not only space, but the shape of time itself, a region where collapse begins, then falters, where pressure breaks, then reforms, where the faint delay becomes something more structured, more patterned, almost architectural. To an outside observer, nothing in the star's appearance hints at such complexity. The surface churns with convection. The star brightens and dims in familiar rhythms. Temperature shifts follow predictable evolutionary curves. But far beneath that calm exterior, deep enough that light itself struggles to escape, lies a layer of matter so dense, so tightly packed around the forming iron core, that its internal physics no longer resembles the rest of the star. This layer is where some astronomers believe the first true fracture in time appears. To understand it, imagine descending into the core of a massive star at the edge of collapse. The pressure is beyond comprehension. Nuclei are squeezed so close that electron degeneracy becomes the last remaining force, preventing total implosion. In this environment, neutrinos, particles that almost never interact with anything, begin to collide, scatter, and accumulate in ways normally reserved for supernova conditions. These neutrinos carry information about the timing of collapse. And in delayed collapse stars, they carry something stranger: inconsistency. Super Kamiokande detectors in Japan once recorded a series of faint, uneven neutrino bursts from a distant red supergiant. They were not strong enough to indicate collapse, nor did they match the periodicity of typical stellar behavior. Their intervals were slightly stretched, just enough to signal that something deep inside the star was falling out of rhythm. IceCube at the South Pole later detected similar bursts from another unstable giant. Again, the timing showed irregularities, not random noise, but a pattern emerging from turbulent matter under extreme curvature. Both instruments hinted at the same thing. There is a region within these stars where the propagation of collapse is slowed, scattered, refracted by layers where time is not flowing uniformly. That region sits just outside the iron core. Here, density grows so rapidly that time dilation intensifies beyond the smooth gradient predicted by classical models. But the intensification is not symmetrical. Magnetic fields twist around the core like braided ropes. Rotational shear drags layers sideways. Neutrino scattering increases opacity. Instead of forming a clean boundary, the star creates a tangled zone, a turbulent shell where time becomes irregular, like water swirling behind a rock. Some theorists call this zone the temporal boundary layer, not a boundary of matter, not a boundary of force, a boundary of moments, a place where regions of slowed time meet regions that have not slowed enough, or have slowed too much, or have been stretched by turbulence into unsteady pockets. Inside the boundary, collapse pulls downward with increasingly unstoppable gravity. Outside the boundary, the star still lives in the moment before collapse. In between, the timelines collide. Pressure waves that try to escape from the collapsing core enter this layer and lose coherence. Their timing breaks apart, their structure dissolves. The collapse signal becomes a blur still present, but unreadable by the layers above. Neutrinos that stream outward from the core scatter unpredictably as they cross the temporal variations. Their bursts reach Earth with subtle distortions that instruments now recognize as signatures of these mismatched regions. Even density waves, ripples of compression that should form the prelude to collapse, flatten, and slow the moment they strike this layer, as if hitting a cushion made not of matter, but of delayed time. This is why the core can begin collapsing while the surface remains unchanged. The boundary shields the star from itself. The physics here grows difficult to describe without metaphor. One researcher compared it to trying to pass a sound through a room where different pockets of air vibrate at different speeds. The sound loses coherence, breaks into fragments, reassembles in distorted form. In the star, collapse is the sound. The temporal boundary layer is the room with uneven air. But something about this analogy misses the scale of the phenomenon. This isn't air, it's time. If collapse tries to propagate outward through inconsistent time flow, the propagation becomes unstable. It may stall. It may spread only partially. It may move inward again. It may ripple in loops that remain hidden from the surface. Inside the boundary, collapse can be happening rapidly, while just outside it, nothing changes. Which means the star can be dying, and not dying. At the same time, light curves pick up the outer echoes of this behavior. Neutrinos pick up the inner ones, but the boundary layer itself remains invisible, detectable only through its effects. Even the star's gravitational signature carries hints of this structure. Subtle variations in its rotational profile mapped by detailed astrometry suggest that mass distribution within certain giants shifts in ways that do not match surface activity. It's as if the interior is moving on a different schedule than the exterior. A timeline hidden beneath the surface. This hidden layer, if real, forces us to rethink what a star is. We are used to seeing stars as fluid bodies governed by pressure, temperature, and gravity. But here, in the delayed collapsed stars, those forces act through the medium of time itself. Time that is uneven, time that has structure, time that may resist alignment. If such a boundary exists, it marks the place where collapse stalls, where signals lose their meaning, where the core's death cannot pass into the living star around it. And if that is true, then the nature of collapse is no longer defined by force alone. It becomes a matter of communication of messages, traveling through a medium unable to deliver them intact. This boundary raises new questions that stretch well beyond the physics of stars. If events require temporal agreement to propagate, what happens when agreement is impossible? Can a collapse remain trapped beneath a layer of time forever? Do the timelines drift apart until collapse becomes a private event within the star, unseen by the universe outside it? Or does something eventually force the boundary to give way? Neutrino scatter patterns hint that the boundary may shift over time. Spectral delays suggest that the surface may slowly feel the strain. Certain irregularities in mass loss hint at internal stress trying to escape. But none of these signs tell us what comes next, because somewhere beyond the boundary, outside this turbulent seam of mismatched moments, the star continues shining with strange stability. Its surface, unaware that the core beneath it might already be falling inward, caught between collapse and the refusal of collapse. And this brings us to the next layer of the mystery, a layer shaped not by time alone, but by a star's ability to outlive its own death in ways we are only beginning to understand. A layer where the whole star becomes a paradox in motion, and where one object above us has already become the most iconic example, a giant whose collapse was predicted, expected, declared imminent, yet still has not come. There is a star close enough, bright enough, ancient enough, that its life has been visible to human eyes since our earliest stories. It glows with a warm, pulsing red, steady yet restless, fragile yet immense. Betelgeuse, the shoulder of Orion, a supergiant so swollen with age that its surface drifts like a slow tide of burning dust. For more than a century, astronomers have known that Betelgeuse is near the end of its life. Its size alone is a confession. Its mass is heavy enough to guarantee a violent death. Its age places it well within the window where collapse should already be unfolding. Everything we know about stellar evolution says that Betelgeuse's heart has been ready to fail. And then came the dimming. In late 2019, Betelgeuse faded dramatically. Not gradually, not gently, abruptly. It dropped in brightness by nearly 40%, a change so significant that even casual stargazers felt the sky shift. Scientists pointed telescopes, ran simulations, recalculated its timeline. Many believed the dimming marked the beginning of the end. A supernova seemed imminent. But the star brightened again. As quickly as it fell, it rose. The light returned. The surface warmed. The panic softened into curiosity. Betelgeuse had dimmed, but not died. Telescopes later revealed a cloud of dust ejected from the surface, a plausible explanation for the fading. But beneath that explanation lingered questions that dust alone could not resolve. Betelgeuse's oscillations showed strange shifts. Its convection patterns slowed. Its surface seemed to move out of sync with its deeper layers. Something inside the star had changed. And though the surface returned to normal, the shape of the brightness fluctuations, the subtle hesitations in its rhythm, carried a familiar signature. The faint delay. It was not pronounced enough to be a collapse, but it was too structured to be noise. too persistent to be ignored. Betelgeuse became the first nearby giant whose behavior matched the hesitation found in the forgotten supernovae stars that should have died but continued shining. A supergiant like Betelgeuse lives fast. It burns through nuclear fuel at a pace that leaves little room for error. By the time it enters the red supergiant phase, its core is already thick with heavy elements, its mass distribution unstable, its convection turbulent. Everything points toward collapse, yet collapse has not come. Deep inside, the iron core may already be forming. Pressure waves from the inner regions show irregularities that resemble the early collapse signal. Neutrino detectors IceCube and Super Cameo Candae have recorded soft fluctuations in arrival timing from Betelgeuse's direction. Nothing strong enough to declare an event, but enough to whisper inconsistency. These signals are not conclusive, but they echo a pattern we have seen before. A core approaching collapse, while the surface remains unaware. Betelgeuse's surface is vast, so vast that light from one side reaches the other in hours. Its convection cells are larger than planets, but scale does not protect it from temporal fracture. In a star this enormous, time dilation can become severe. Add turbulence, magnetic knots, rotation, and density waves, and the internal synchronization becomes fragile. Imagine a core entering the first breaths of collapse. Imagine the pressure waves attempting to travel outward, only to strike a temporal boundary layer, like the one seen in other delayed collapse stars. The waves scatter. The surface remains untouched. Meanwhile, the star continues shining, its outer layers unaware that the core beneath them is changing. A star can hide many things, but hiding collapse is something different. This leads to a possibility both extraordinary and uncomfortable. Betelgeuse might already be collapsing internally, just not in the timeline its surface occupies. The 2019 dimming, when viewed through this lens, becomes more than dust. It becomes the surface responding to something it could only feel indirectly: stress, transmitted imperfectly through tangled timelines, a message blurred by temporal viscosity, a ripple that reached the star's exterior without revealing its true origin. Some models predict that Betelgeuse should have collapsed thousands of years ago. Others extend its life only a few decades into our future. But all models assume clean communication between layers. All assume that collapse, once begun, spreads seamlessly. The faint delay in Betelgeuse's brightness challenges that assumption. It tells us that parts of the star may be evolving out of step. That time within Betelgeuse may be drifting, fragmenting into layers, moving at different speeds. That some layers may have already felt the moment of collapse, while others have not yet lived through the events that lead to it. This mismatch could explain the strange asymmetry in Betelgeuse's recent surface behavior. Thermal maps show hot and cold patches shifting in ways that do not align with convection patterns. Mass loss regions appear in unexpected geometries, as though guided by internal structures whose timelines do not match their surroundings. Even the star's pulsation period has grown irregular. Not chaotic, just slightly off. A heartbeat sliding out of alignment with itself. This is exactly the kind of temporal drift expected when collapse signals cannot pass cleanly through the star's layers. The outer surface, still living in its earlier moments, pulses on one rhythm. The inner regions, closer to collapse, pulse on another. Their disagreement becomes the hesitation we observe from Earth. Betelgeuse's immense size magnifies the effect. The larger the star, the more layers time must travel through. The more layers time must travel through, the more opportunities for temporal fracture. And the more fracture, the greater the delay. If Betelgeuse has entered such a state, then its collapse, should it truly begin, may not reach the surface quickly. The explosion may be trapped in slow time, unfolding internally, while the outer layers continue shining for years, centuries, or even longer. This is not the popular image of a supernova. It is something quieter, more complex, a death that refuses to gather itself into a single moment. Astronomers continue to watch Betelgeuse closely, mapping its brightness down to the smallest fluctuations. They know what the data means. They recognize the patterns. They see the delay, even if they do not call it temporal inertia or boundary layer fracture. They acknowledge the mismatch between the star's interior behavior and its outward appearance. Betelgeuse is teaching us something fundamental, that a star may outlive its own death simply because time inside it has not yet agreed to end. And this realization reshapes more than our understanding of Betelgeuse itself. It reshapes how we measure collapse, how we interpret light, how we read the sky. Because if Betelgeuse can begin collapsing in slow time while appearing unchanged in our own, then every massive star we watch is more mysterious than we knew. The delay is not just an observational quirk. It is a window into the places where collapse becomes tangled in time, and where endings can stretch so far that the universe forgets they have already begun. And just as this possibility deepens, another question begins to rise from the structure of the data, forming quietly at the edge of everything we've seen so far. If Betelgeuse can outlive its own collapse, then what happens in the moments just before collapse should be impossible. Moments where the timing of nuclear burning itself begins to shift, stretching processes that should last days into years, and years into lifetimes, as if the star is trying to rewrite the tempo of its final breaths. Before the universe can hear them, there is a stage in the life of a massive star, so brief, so intense, so final that it is often described not as a phase, but as a countdown. Silicon burning, the last breath before collapse, a furnace collapsing under its own heat. In ordinary stars of great mass, this stage lasts no more than a handful of days, sometimes less. It is the shortest chapter in a star's evolution, the final flicker before gravity erases the boundary between matter and implosion. But in the stars that refuse to die, silicon burning does something it has no right to do. It lingers, not for hours, not for days, but for years, and in the strangest cases, even for decades. This contradiction is one of the most disturbing signatures of delayed collapse stars. The nuclear reactions in a silicon-burning core produce enormous amounts of energy, but they also drain the star of its last reserves. The process runs so hot, so fast, that the core should consume its silicon fuel rapidly, racing toward the formation of an iron core and the collapse that must follow. There is no known mechanism that slows it, no known force that drags it out, no known physics that stretches a days-long process across human lifetimes. And yet, the evidence stands. In certain red and blue supergiants, spectral indicators associated with silicon fusion remain present far beyond their predicted window. Surface vibrations tied to the deep interior show cycles so slow that they contradict every model of end-stage nuclear burning. Temperature echoes in their radiative zones, faint but measurable, repeat in rhythms inconsistent with their age. It is as though the core continues its frantic burn, but the universe around it measures time differently. Stars like these behave as if the silicon burning phase, normally the shortest, has become one of the longest. A phase stretched across temporal inconsistencies so deep, so quiet, that only the subtle drift of surface light can reveal them. To understand how impossible this is, imagine standing in front of a candle whose flame should consume the wick in minutes, but somehow continues burning for years, unchanged. Not because the fuel is infinite, but because the speed at which the flame consumes the wick has slowed without explanation. For these stars, the flame is silicon burning, the wick is time, and something inside the core is stretching that time. Deep detector networks like IceCube pick up neutrino patterns, suggesting prolonged high-energy interactions consistent with silicon fusion. But the duration of these patterns does not match the physics. It's as if the core is burning in slow motion, still racing through reactions at unimaginable intensity, but doing so inside a timeline that moves differently than the one we see from outside. The conflict becomes sharper the more we look. In classical models, silicon burning pushes the core to instability so quickly that collapse is almost unavoidable. Iron builds. Pressure fails. Gravity strengthens. The star's end becomes an accelerating inevitability. But observationally, certain stars remain suspended in this state, never gathering the final momentum required for collapse. Their cores behave like engines revving at maximum power, without moving forward. This is the point where astronomers began to suspect that prolonging silicon burning might be a side effect of the temporal boundary layer described earlier. If collapse inside the star unfolds in a slowed timeline, then the reactions feeding that collapsed silicon fusion would also appear slowed from our perspective. The reactions might be occurring normally inside the core's own timeline, burning through silicon at the proper rate, but the translation of events through uneven time flow would stretch them across longer intervals. The surface, living in a faster timeline, would see a process meant to last days unfold over decades. This mismatch becomes even more profound when examining light curve drift. A star's brightness should tighten rhythmically as silicon burning nears its end. Instead, certain giants exhibit a loosening of rhythm, an elongation where the peaks and valleys of luminosity pull farther apart, guided by a metronome that seems to grow more lethargic each year, as if the star is breathing more slowly, even while its core burns more violently. The contradiction is staggering, yet it fits the pattern of delayed collapse perfectly. The deeper processes accelerate, the outer layers decelerate, and the star becomes a tangle of mismatched speeds. Multi-observatory studies of several candidates showed that their estimated core temperatures derived indirectly from spectral modeling fluctuated too slowly to match models of silicon depletion. The temperatures responded as though the core was stuck, not frozen, not dead, just slowed, suspended in a moment stretched wider than it should be. This leads to an unsettling possibility. The core may already be entering collapse while still burning silicon. Normally, collapse begins only after silicon is fully consumed. But if the core is falling inward in a slowed timeline, while the silicon burning shell still exists in a faster timeline, then the two events, burning and collapse, may overlap, passing through each other imperfectly, failing to synchronize. The star enters a paradoxical state where collapse is trying to begin in one moment, while the prerequisites for collapse still exist in another. A contradiction, not of physics, but of timelines. Inside the star, collapse might feel minutes old. Outside the star, silicon burning might feel decades old. Both truths coexist because time inside the star no longer flows as a single entity. Even the gravitational field hints at this. Betelgeuse's subtle rotational drift. A.G. Carinet's oscillation lag. Red supergiants showing mass loss signatures inconsistent with their nuclear stage, all pointing toward a deeper truth. When collapse tries to propagate through uneven time, the star experiences both the before and the after at once. This makes silicon burning appear prolonged, but the prolongation is not real. The moment itself has been stretched, which leads to the quiet question forming now, soft but unavoidable. If the final nuclear stage of a star, normally just days, can become an entire chapter of its life, then what does that say about the meaning of duration inside a collapsing star? What does a timescale even mean? When the clocks are no longer tied to the same reality, a star in prolonged silicon burning is not merely delaying collapse. It is revealing that collapse is not a single point at all, but a shape, a region of time, a shifting boundary the star must cross together. And if the star cannot align itself across that boundary, if no single moment can gather all its layers into agreement, then collapse becomes something more fluid, more uncertain, more fractured. And in that fracture lies the doorway to a realization more profound than the delay itself, a realization that begins to appear only when we stop treating time inside the star as a single river, and start asking whether the river might be splitting into separate channels that no longer meet. A realization that will shape everything that follows in the next whisper as we begin to see that the star is not failing. It is diverging. There is a moment in the study of delayed collapse stars where the old frameworks stop holding. A moment when stretching, slowing, and hesitation are no longer enough to describe what is happening inside these giants. A moment when time itself, instead of bending smoothly under gravity, appears to divide, not into faster and slower, but into separate flows coexisting, touching, but not fully merging. A star becomes not a single timeline, but a cluster of them. The first hints of this came from the mismatch between silicon burning duration and the behavior of the deeper core. The deeper processes seemed to be living through minutes. The outer layers lived through years, and the layers between them drifted across intervals that matched neither. It was no longer dilation. It was no longer viscosity. it was fragmentation. In classical astrophysics, the timeline inside a star is assumed continuous. Even under intense gravitational curvature, the flow of time changes gradually. But in the delayed collapse stars, that gradient seems to break into discontinuous patches, as if the ocean of time has fractured into eddies. These eddies do not rotate like fluid, they rotate in momentum. Moments circulate. Moments detach from each other. Moments fold and refold around turbulent structures. Some theorists once dismissed the idea entirely. Time cannot split, they said. But the observations kept accumulating. Oscillation patterns in certain red supergiants show not just delays, but double delays. One signal arriving later than expected, another arriving earlier. Two timelines superimposed. Two rhythms emerging from the same event. The surface brightness drift of Betelgeuse exhibits weak, but consistent frequency-splitting peaks, arriving in pairs, separated by intervals too precise to be noise. A star with one pulse seems to be pulsing on two clocks. And in the neutrino data, the most startling signature. Bursts that should have been single events appear as clusters, stretched in one direction and compressed in another, like a message recorded by two different moments overlapping. It is as if collapse sends its signal outward along more than one path through time, paths that diverge inside the star and only partially reunite on their way out. This is the phenomenon now called internal temporal splitting. A star contains multiple versions of now. They coexist in layers. They interact, but imperfectly. And collapse, which should be a unified event, becomes scattered across these fragmented timelines. Deep inside, near the foundation of the iron core, time is compressed. Moments fall into each other. Events accelerate toward collapse. Farther out, time loosens. Moments drift. Events stretch. But between these regions lies the strangest territory. Zones where time neither accelerates nor slows smoothly, but instead folds, creating local pockets where a process begins twice, ends twice, or fails to end at the expected moment. These pockets behave like temporal mirrors. A signal enters them, splits into two variations, one moving through a slowed domain, the other through a domain nearer to the core's accelerated moment, and emerges at the boundary carrying both histories. We see those histories in light. We see them in neutrinos. We see them in the oscillations of the star's surface. But the star itself does not see them in the way we do. It feels them. Temporal splitting introduces conflict into the star's structure, not of force, but of timing. Some regions respond to collapse. Some respond to the moment before collapse. Some respond to both, pulling matter and heat into patterns that should not coexist. It is here, in the split regions, that unusual convection patterns form cells that reverse direction unpredictably, layers that drift against pressure gradients, thermal zones that repeat cycles with irregular length, not chaotic, just doubled, ghosted, two versions of evolution interweaving. This behavior is not simply instability. It is the interior of the star trying to choose a timeline and failing. The deeper core, falling inward through compressed time, attempts to propagate, collapse upward. The outer layers, stretched across long moments, lag behind. The split layers in between oscillate between responding and not responding, as if trapped between two different future outcomes. This gives rise to what looks like false collapse events, internal failures that begin but do not finish, because collapse in one timeline cannot synchronize with collapse in another. To us, from Earth, the star appears stable, but within it, collapse may be happening repeatedly, each attempt fading when the timelines fail to converge. This leads to the first true turning point in our understanding. Delayed collapse may not be a matter of resistance, it may be a matter of disagreement, not between forces, but between moments. A star cannot collapse until all of its timelines align enough to permit a unified event. If the timelines remain split, the collapse remains fragmented, distributed across temporal domains that cannot complete the process together. This reframes everything we have seen: the faint delay in brightness, the hesitation in neutrinos, the prolonged silicon burning, the stalled collapse signals. They are not anomalies. They are symptoms of a star whose timelines have drifted so far apart that collapse cannot become singular. The star is falling inward in one timeline. It is resisting collapse in another. It is preparing to collapse in a third. And the boundaries between these versions of itself are porous, but not permeable enough. The result is a star in limbo, not because physics has paused, but because time has fractured into branches that no longer share the same sequence of events. Some astronomers describe it like this: a dying star becomes a constellation of its own moments. Not poetic metaphor, a descriptive truth. Its interior is a map of diverging nows, each connected loosely by turbulence and pressure waves, each holding its own version of the collapse. And this raises a question that cannot be avoided now. If a star contains multiple versions of time, which version does the universe see? Which version determines when the star ends? Which version defines the moment of the supernova? The answer may lie in how these timelines eventually merge, or fail to merge. And that leads us, quiet as a breath, drifting between layers of heat, toward a deeper inquiry that waits just beyond the horizon of this chapter. If a star can split into multiple timelines, what happens to its identity? The thing we call the star itself. When each part is living through a different moment of its own ending, the next whisper begins inside that question, where identity dissolves into layers of time, and where the collapse of a star becomes indistinguishable from the collapse of its own continuity. When time inside a star begins to split, something subtle and profound happens, something deeper than physics, quieter than collapse, stranger than light that hesitates. The star begins to lose the simple unity we take for granted. It stops being one thing. It becomes a tapestry of selves, each living through a different moment of its own dying. And that raises a question we rarely ask in astrophysics. What does it mean for a star to reach its ending? If its ending is no longer a single moment, we tend to imagine stellar death as clean, decisive, a turning point, a final threshold, the last step on the staircase of nuclear fusion. But inside a delayed collapse star, that staircase dissolves. Each step drifts into another timeline. Each threshold broadens into a region. The collapse does not reach the boundary of definition. It hovers near it, circles it, approaches it from multiple timelines that do not intersect. The star continues shining, not because it refuses to die, but because death has lost its shape. In these conditions, collapse is no longer an event. It is a conversation the star is having with time, a conversation in which none of the participants are speaking at the same pace. One region of the star may already be inside the moment of collapse, compressed into gravity's deep well. Another may still be burning fuel in a slower, older moment. The split layers between them may live in the uncertainty between those moments. And the star, as a whole, becomes a being stretched across its own divergent experience of existence. This is not metaphor. It is the literal effect of temporal splitting. A star cannot maintain a single identity if its internal time cannot maintain a single sequence. Astronomers have begun to notice this in small ways. For instance, some stars exhibit 2 or 3 distinct pulsation periods, not harmonics, not thermal modes, but independent rhythms that drift in and out of phase like separate heartbeats. In classical physics, these beats should converge or stabilize. But in delayed collapse stars, they behave as if anchored to different layers of time. Imagine listening to a symphony played by instruments that do not share the same second. Each part is true to itself, but the whole becomes something else. This fragmentation leads to a philosophical tension in the nature of endings themselves. If the star is living through multiple nows, how do we define the moment of collapse? Is it the moment the core begins to fail? The moment the outer shell responds? The moment the universe receives the light of the explosion? These questions do not have answers, not because they are abstract, but because the physics has outgrown the single moment model. Collapse becomes a region, not a point, a drift, not a fall, a negotiation between timelines that may never align. Temporal inertia, the resistance of time to change, holds the star in that negotiation. Temporal splitting divides the negotiation into multiple arguments. The boundary layer delays everything trying to pass through it, and the star remains suspended. This suspension is not stasis. It is motion happening in different directions at once. A collapse that has started in one slice of time and stalled in another. A momentum toward ending that cannot find a unified path. Some astrophysicists refer to this as the interval of divergence, a period where the meaning of the star becomes distributed across its internal moments. The star still glows, still orbits, still radiates heat into space, but internally, it no longer shares a single identity. To describe this, we must shift our perspective from events to agreements. Every stellar ending is fundamentally an agreement between the star's layers. The outer layers must agree that collapse is occurring. The middle layers must carry the signal. The core must complete the transition. Time must deliver each layer to the same moment. Without that agreement, collapse is incomplete. A star may contain collapse. A star may begin collapse. A star may repeat collapse. But it cannot complete collapse until every timeline within it converges enough to produce a single moment. This realization unsettles the simple picture of stellar death. For billions of years, stars live as unified beings, every layer connected by the same flow of time. But as they near their end, that unity becomes fragile. Time inside them becomes layered, staggered, full of micro delays and hesitations. A star may spend millennia in that fractured ending, shining long after the core has begun to fall. And here, in this suspended state, a deeper philosophical idea emerges. The ending of a star is not the collapse itself. The ending is the moment its timelines surrender their differences. In other words, a star does not die when physics dictates. It dies when time inside it agrees. This agreement is not guaranteed. Some stars resist alignment. Their timelines drift farther apart, like threads pulling loose from a woven fabric. The star becomes more a collection of temporal echoes than a single object. But even in divergence, something binds them. Gravity still shapes them. Pressure still pulses. Light still escapes. The star remains one star, even if one part is living seconds while another lives decades. This coexistence of mismatched time flows suggests something profound about the nature of identity in astrophysical objects. If a star can remain itself while containing multiple timelines, then self is not tied to simultaneity. Self is tied to continuity, the ability of the star's layers to remain connected, even if their internal moments no longer match. And this continuity survives until the very end. Even in the most fractured stars, the outer layers still feel faint traces of the inner struggle. Brightness still carries delayed information. Neutrinos still carry distorted signatures. Oscillations still echo 2 or 3 timelines at once. These echoes are the star's last attempt to remain whole, to coordinate the pieces of itself long enough to complete the final transition. But the more the star tries, the more its timelines push against one another. And the more they push, the more the ending stretches. Which leads us to a deeper, quieter question, one not about stars, but about time itself. If a star's ending requires its timelines to converge, could a universe filled with multi-layered time contain objects that never reach that convergence at all? Could some stars be trapped in an infinite pre-collapse, burning through fractured moments, without ever entering the singular now that becomes the supernova? We do not know. We only know that delayed collapse stars drift dangerously close to this possibility. Their light suggests perseverance. Their interior suggests divergence. Their timelines suggest a slow unraveling of unity. And somewhere inside that unraveling, the meaning of ending becomes difficult to define. Not because the star refuses it, but because time itself cannot find a door through which all its layers can pass at once. This tension between unity and divergence, between identity and fragmentation, between collapse and the refusal of collapse, leads naturally to the next question. Rising from the physics, if a star can lose the unity of its own moment, could the universe itself also carry mismatches in its timing, subtle drifts in its own memory, places where cosmic events do not line up the way we assume they do? There are signs, there are whispers, there are observations that do not fit cleanly anywhere yet, and as we move toward them, the boundaries between stellar time and cosmic time begin to blur in ways that carry us gently, inevitably, into the next quiet fold of this mystery. When a star's timelines drift apart, We can explain it hesitantly through pressure, gravity, turbulence, and the impossible weight of collapse. But the deeper implication is harder to ignore. If time can fracture inside something as ordinary as a star, then what guarantees that the universe itself holds time together cleanly? This question began quietly, almost as an afterthought, in the minds of astronomers comparing observations of delayed collapsed stars. Noticing delays was one thing, explaining them through internal mechanisms was another, but a few researchers noticed patterns that did not belong to the stars at all. They belonged to the cosmos around them. Light arriving from the same region of space seemed to carry discrepancies not entirely accounted for by stellar behavior. Neutrinos from unrelated sources displayed micro-lags that did not match predictions. Even gravitational wave echoes, rare, soft, near the threshold of detectability, showed signs of subtle misalignment, as though the universe itself had forgotten the order in which some events occurred. Not incorrectly, not chaotically, just imperfectly. A faint misremembering. Cosmic memory, if such a thing exists, does not operate like human recall. It is not about forgetting details or reshaping stories. It is about the sequence of events woven into space-time, what came before what triggered what, how the fabric stores cause and effect. If that weave becomes stretched or disturbed, the universe may still function, but the timing of events can appear inconsistent to those who measure them. This is not speculation built from metaphor. It is built from evidence that refuses to align. For example, certain neutron stars that have undergone starquakes show rotational adjustments that disagree with their thermal signatures by fractions of seconds too large to attribute to measurement noise. Pulses arriving from magnetars exhibit small timing gaps that appear and vanish unpredictably, as if the universe shifts the spacing between beats without adjusting the beats themselves. Cosmologists once attributed these inconsistencies to local gravitational effects, dark matter clumps, warped spacetime, interstellar plasma. But the anomalies kept appearing where such influences should not dominate. The misalignments were too subtle to rewrite physics, but too consistent to dismiss. They resembled, in tone and texture, the hesitation inside delayed collapsed stars. A cosmic scale, faint delay. If the universe carries its own temporal inconsistencies, then stars drifting inside, those inconsistencies are not anomalies. They are expressions of a larger unevenness. Their hesitation becomes a mirror of the cosmos they inhabit. The idea unsettles the straightforward picture of cosmic time we typically teach, a single, universal arrow stretching from the Big Bang to now. Time, in that picture, is uniform, reliable, smooth. But general relativity already tells us that time depends on gravity. Quantum theory suggests it depends on information, and delayed collapsed stars whisper that time may also depend on continuity, the ability of a system to maintain agreement between its parts. If a star can lose that agreement, what prevents the universe from losing it too? This leads some physicists to propose an unusual framework: cosmic temporal slip. The idea that space-time may evolve not smoothly, but through tiny steps, each holding a slightly different memory of what came before. Imagine a vast ocean where each wave carries a slightly altered recall of the waves behind it. The ocean still moves forward. The waves still crash. But the history that pushes each new wave is not perfectly aligned. Beneath the rhythm lies a mismatch. If the universe holds such mismatches, we would expect to see them first in systems extremely sensitive to time flow, stars at the edge of collapse, pulsars with precise rhythms, particles carrying information across large distances. And that is exactly where the anomalies appear. A delayed collapsed star, then, might not only contain a fractured timeline, it might exist in a region where cosmic time itself is drifting. A star built on drifting time would not reach collapse cleanly. A collapse signal entering such a region would struggle to maintain coherence. Even the memory of collapse, the order of internal changes, could be altered as it passes through uneven cosmic time. This may explain why some supernovae signatures arrive late, why gravitational wave echoes from certain events appear stretched, and why light from a collapsing star might carry a hesitation that is not solely due to internal processes. The star hesitates because the universe hesitates around it. Some researchers suggest that space-time curvature near massive objects can store traces of previous events, like grooves carved into the fabric by the history of motions and collapses. If so, the universe could remember incorrectly, replaying sequences slightly out of order, and stars living within those grooves would inherit those distortions. This idea, though speculative, speaks to something deeper. Cause and effect may not be as absolute as we believe. If time inside stars drifts, and time across the cosmos drifts, then the boundary between stellar chronology and cosmic chronology becomes porous. Observations support this strangely well. For example, in several distant supernova remnants, the distribution of ejected materials does not match the expected timeline of collapse. The explosion seems to begin unevenly, as if different parts of the star exploded in different orders. Even after the event is over, the remnant carries the imprint of temporal misalignment. Imagine an explosion whose beginning and ending overlap in unpredictable ways. A detonation unfolding through a slightly tangled sequence of moments, a bright event recorded by the universe in a non-linear memory. This phenomenon resembles the faint hesitation seen in delayed collapse stars, but extended across light years. Another clue lies in the cosmic microwave background. Certain small anisotropies, deviations in uniformity, have timing implications inconsistent with inflation models. Some physicists interpret these as leftover scars of ancient temporal slips, regions of the early universe where time may have flowed unevenly before settling into the more uniform structure we observe today. If time once fractured in the early universe, it might still do so in smaller pockets now, and delayed collapse stars may simply be the places where this ancient behavior resurfaces. This links stellar physics to cosmology in a way that was not obvious before. The star's prolonged silicon burning, its mismatched timelines, its failure to collapse coherently. These may not be solely internal phenomena. They may be the star responding to cosmic time that has begun to lose its perfect memory of sequence. A star living inside a universe that cannot keep its own story straight would struggle to complete the final chapter of its life. This notion carries a quiet philosophical weight. If the universe misremembers its events, then endings may be softer than we imagine, drawn out, stretched, blurred at the edges, more like fading recollections than sharp conclusions. And in this softening, the distinction between what has happened and what is still happening grows thinner. A delayed collapse star becomes a witness to that thinning. Its hesitation is not only internal, it is cosmic. It is the universe drifting through itself, forgetting just enough of the order of things to leave stars suspended between moments. And as this idea unfolds, another begins forming at the edge of understanding. If the universe misremembers time, then light, our only messenger across the dark, must carry that misremembering with it, which raises a deeper question for the next whisper. If light can drift through uneven cosmic memory, what does that do to the pulse of collapsing stars? Those slow, impossible rhythms that reach us long after the stars themselves should have fallen silent? The answer begins where the faintest pulses stretch, not in the star, not in the core, but in the space between moments. Light has always been our cleanest witness. It does not argue. It does not forget. It carries whatever truth it was born into: temperature, motion, gravity, distance across the dark without hesitation. At least, that is what we once believed. But when a star nears collapse and its timelines begin to drift, even light, the simplest, purest messenger, starts to inherit the confusion of the moment. Its wavelengths stretch in ways that no Doppler shift can explain. Its timing drifts in ways no turbulence can justify. Its brightness pulses with a rhythm that feels less like a signal and more like a memory replayed imperfectly. Light begins to echo collapse before collapse reaches the surface, not through flashes, not through explosions, but through a distant, softened rhythm, a slow pulse, as if collapse itself is trying to breathe through the star. This pulse is not a periodic oscillation. It is not a stellar heartbeat. It is not a vibration of pressure waves. It is something quieter, something that seems to sit between the physics we understand, shaped not by force, but by the misalignment of time. When collapse begins inside a star, the core tightens in gravitational moments far shorter than any process above it. Those inner contractions produce bursts of photons and neutrinos, brief, sharp, unmistakably violent. But as those signals travel outward into regions of stretched time, they lose their immediacy. Their intensity diminishes. Their timing lengthens. What was a single beat in the core becomes a drawn-out shimmer by the time it reaches the surface. The star does not brighten, it wavers, a living hesitation woven into light itself. Kepler and Tess have recorded these wandering rhythms in several luminous blue variables. Small dips not tied to convection, small rises not tied to temperature, tiny distortions synchronized with nothing except an unseen engine deep inside. The distortions appear on monthly scales, though the reactions causing them should occur in minutes. Light is stretching a shorter story across a longer timeline. In stars approaching collapse, this slow pulse becomes more pronounced. Brightness peaks arrive slightly too late. Valleys arrive slightly too early. The rhythm drifts outward like ripples passing through uneven water. The same signature seen in delayed collapse stars, but now repeating in a pattern gentle enough for instruments to follow. The pulse is not constant. It breathes. Sometimes it is wide, drawn out, drifting like a shadow. Sometimes it tightens, almost aligning with surface processes before slipping away again. The star glows as though caught between two metronomes, one defined by physics, the other defined by fractured time. These light curves do not show collapse. They show collapse trying to reach the surface. What we see is not the event itself, but the memory of the event, stretched across mismatched timelines. Imagine a landscape struck by a distant thunder, but the air between you and the storm distorts the sound so deeply that the thunder arrives as a long, low murmur rather than a single crack. The event remains sharp, but the medium smears it. Light coming from a delayed collapse star is that murmur. The deeper parts of the star continue collapsing on their own timeline, moments compressed into violent instants, while the outer regions remain suspended in timelines stretched into long breaths. Light crossing this divide becomes imprinted with both experiences, the intensity of collapse and the delay of uneven time. The result is a slow pulse whose origin is not energy but chronology. This pulse grows stranger, the closer the star approaches its undefined ending. In some stars, brightness dips arrive in pairs. Two hesitations separated by a gap that does not match any thermal or convective process. Two pulses from one moment, split across two incompatible flows of time. In others, the slow pulse appears to reverse direction, as though the star brightens in response to a dimming that hasn't happened yet. These reversals match the behavior predicted by temporal splitting, light escaping from regions where collapse timelines have folded back on themselves. To an observer, the star flickers softly. To the universe, the star flickers twice. To itself, the star flickers across branches of time that no longer converge. We are not seeing the star change. We are seeing the star try to agree with itself. The slow pulse becomes the closest thing to a language collapse can speak before it happens. It is the only trace of communication left between the core that is falling inward and the layers above it that still believe they have time. The star is telling itself that something is happening. The message simply cannot cross the fractured medium intact. Even gravitational modeling shows faint correlations with these pulses. The star's shape does not distort, not noticeably, but the slight drift in outer layer density, measurable only through extremely precise astrometry, rises and falls with the same quiet rhythm. The pulse is affecting the way matter arranges itself on the star's surface. Light is echoing collapse, and the surface is echoing light. This feedback loop has profound implications. It suggests that the slow pulse is not merely a signal escaping the star. It is a negotiation unfolding within it. A star can only collapse as one, but when its timelines disagree, collapse becomes fractured. The slow pulse is the artifact of that fracture, the star repeating the moment of collapse until its layers can find agreement. This rhythmic searching, this repetition of a moment not yet shared, gives these stars their strange serenity. They glow as if untouched because the parts of them that are touched exist in a different moment entirely. And in this shimmering balance between moments, a deeper question emerges. If light can stretch, collapse into a slow pulse that outlives the event itself, then what is a supernova? Is it the collapse that defines it? Or the convergence of timelines that finally allows collapse to become visible? Perhaps the explosion is not the moment the star dies, but the moment its timelines reunite. A supernova may be less the destruction of a star, and more the reconciliation of its divergent selves. And if this is true, then the slow pulse is the precursor. The breath before agreement, the shimmer before alignment, the quiet rehearsal of an ending, waiting for all versions of the star to arrive. It softens, it lengthens, it drifts, not toward collapse, but toward cohesion, toward a single moment. And yet, even this thought is only another layer in a deeper structure beginning to reveal itself. If light hesitates when passing between timelines, what happens to matter? To the iron boundary? To the very architecture that collapse must cross? Because in the regions beneath the slow pulse, there is a boundary where collapse strains to pass, a boundary that thickens as the star drifts further from temporal unity. A boundary we must now descend into. In the next whisper, where time, matter, and collapse meet in a strange equilibrium that holds the star on the edge of its impossible endurance. There is a place inside a dying star where collapse should be absolute, a place where gravity becomes so overwhelming, so uncompromising, that the iron core should crumble inward without hesitation. A place where pressure, even in its most exotic forms, can no longer resist what the mass demands. And yet, in delayed collapse stars, that place does not behave as expected. Instead of folding inward as a single unit, the iron core develops a strange boundary, a transitional shell where collapse begins, only to stall, weaken, diffuse, and then return in distorted form. A collapse that refuses to cross the threshold, a threshold that refuses to allow collapse through it. It is here, in this narrow, unseen region, where the star becomes divided not only by its layers, but by its moments. To approach this boundary, imagine descending from the turbulent convective layers into the radiative zone, then into the narrow, dense region surrounding the iron core. Temperature rises, density rises, time slows, but the slowing does not follow a clean curve. It ripples, like heat on pavement. It thickens, then thins. It folds around magnetic structures. It clings to turbulence and releases from it. This uneven slowing creates the first sign of the boundary, a mismatch between the internal moment when collapse starts and the moment the layers above it can receive that information. Pressure waves born in the collapsing core should race outward, delivering the news of the star's failure. But the boundary catches them. The waves hit regions of delayed time, and their frequency shifts. They flatten, they blur, their coherence fails. Instead of a sharp directive collapse, now the signal arrives as a softened vibration, stripped of the clarity needed to trigger the next stage. Light from deeper layers undergoes the same fate. Its timing stretches, its path bends. It emerges distorted by the chronology of the boundary, even if its energy remains intact. Neutrinos, normally indifferent to matter, behave unusually here as well. Ice Cube and Super Kamiokande have recorded bursts that appear too early and too late simultaneously, an impossibility unless the neutrinos were created in regions of differently flowing time. Every messenger that tries to cross the boundary becomes tangled. Nothing passes through it unchanged. Nothing carries the pure moment of collapse outward. The star becomes internally opaque not in light, but in time. This boundary is not thick. It may span only a fraction of the star's radius, yet it governs the entire destiny of the collapse. Matter inside the boundary is falling inward through compressed moments. Matter outside the boundary still exists in the slower rhythm that remembers stability. And the boundary itself becomes a membrane between collapse and not collapse, the most fragile, most critical region in the star. In classical models, collapse propagates outward because conditions everywhere align with the same timeline. But in delayed collapse stars, the boundary interrupts that unity. The collapse cannot cross. The star remains in a limbo defined by a thin seam of mismatched moments. Some physicists model the boundary as a temporal gradient, others as a discontinuity, and a few as a standing wave in time, not oscillating in space, but oscillating in how moments stack against each other. Whatever it is, the effect remains the same. Collapse enters, weakens, and fails to leave. Matter behaves strangely within this region. Simulations running on supercomputers show compression waves looping inside the boundary, as if bouncing between mismatched time flows. The waves do not escape. They rotate, caught in a chamber whose walls are made not of force but of misaligned chronology. This looping may explain why some delayed collapse stars exhibit repeated internal collapses, brief failures that trigger, fade, and repeat without producing a supernova. To the core, collapse may have occurred many times. To the surface, collapse has never happened. A star that collapses repeatedly inside itself, and yet continues to shine, violates the timeline of traditional astrophysics, but fits perfectly in a universe where time can split and hesitate. Another mystery emerges from this boundary. The iron core does not always grow in the expected pattern. Sometimes it appears smaller than the star's age and mass would predict. Other times it appears larger. Both findings are paradoxical, unless the growth rate itself is unfolding across divergent timelines. An iron core growing in accelerated time will appear older than it should. A core growing in delayed time will appear younger. Both can be true in one star, if the boundary prevents the outer layers from experiencing the same moment as the inner core. Even gravity reveals the boundary's existence. Precise measurements of stellar wobble show inconsistencies, as if the center of mass shifts slightly depending on which part of the timeline dominates the observation. Gravity itself appears to pulse softly, mirroring the slow pulse of collapsing light, but arising from deeper and heavier origins. A star with a pulsing center of mass is a star negotiating its own collapse across timelines that do not agree. This boundary creates a profound philosophical tension. Where is the true center of the star? Is it the collapsing core? Is it the stable outer layers? Or is it the boundary where neither reality fully holds? Identity dissolves here. The star becomes a layered argument between different versions of its own moment, and that argument never resolves cleanly. Not until something forces all timelines into alignment. Not until collapse becomes unavoidable. Not because physics demands it, but because time can no longer remain fractured. But what forces the alignment? Pressure? Gravity? Temperature? Or some deeper need within time itself to settle into coherence? We do not know. The boundary keeps the answer hidden. Yet, as we follow this hidden structure deeper, another thought begins forming, quiet and unsteady. A thought about stars that seem not to resist collapse, but to wait. Wait for timelines to converge. Wait for internal echoes to match. Wait for the boundary to thin. Wait for something that has nothing to do with force and everything to do with agreement. This waiting is not passive. It is a tension carried across misaligned moments, a stillness that is not still, a balance that is not stable. And as we approach this next fold in the mystery, the question rises softly. If collapse is held back, not by strength, but by waiting, what is the star waiting for? The next whisper begins in that waiting, in the quiet, suspended breath that holds the star on the threshold of an ending that cannot quite arrive. There is a silence inside a dying star that does not belong to physics. It is not the silence of cooling, not the silence of stalled collapse, not the silence of energy lost to space. It is the silence of waiting, a stillness that forms when a star realizes, in its own way, that collapse cannot proceed until time inside it chooses to agree again. We do not often think of stars as capable of waiting. They burn, they fuse, they expand, they collapse. Their lives feel mechanical, inevitable, ruled by equations older than galaxies. But when their timelines fracture, the equations loosen, processes drift, moments slip out of order, and a strange kind of pause appears. Not a pause in motion, but a pause in meaning, a pause in the star's ability to interpret itself. In delayed collapse stars, this pause is everywhere. Though we do not always recognize it, The iron core trembles at the threshold of failure, yet refuses to fall inward in a single event. The boundary layer catches collapse signals, yet does not allow them to disappear. The outer layers pulse in long, slow breaths, yet feel no catastrophe beneath them. The star is suspended between futures, one collapsing, one enduring, one trying to converge. Inside this suspension, the star behaves like a system, listening for something it cannot define. It drifts through mismatched timelines that do not share a common moment, each layer alert to a shift that has not yet arrived. It is the first time in stellar evolution where cause and effect become negotiable. A star normally burns fuel in one moment and responds structurally in the next. But, in fragmented time flow, the cause may occur in a region living through faster moments, while the effect must propagate into regions where moments are slower. The effect becomes delayed not because the star resists change, but because the moment of change has not yet reached that part of its identity. The result is the star's unique form of waiting, not for energy, not for pressure, but for agreement. Agreement between layers, agreement between signals, agreement between timelines that have wandered too far apart. Astronomers, reading only the surface, call this extended stability, as though the star remains intact simply because its outward forces continue to balance its inward ones. But nothing about this balance is stable. It is a balance written in tension, a balance made of mismatched beats, a balance that holds not through strength, but through unfinished processes stretched across divergent time. If you were to describe this waiting in human terms, you might call it anticipation, the sense of something forming in the near future, too close to ignore, too far to touch. Stars do not think, but their physics creates shapes that resemble thought. Their delays resemble hesitation, their pulses resemble longing. Their fractured timelines resemble indecision, not conscious indecision, but the structural impossibility of acting before all parts can agree to act together. In this sense, a delayed collapse star is not resisting its ending. It is anticipating its moment of unity. It waits because collapse cannot proceed until all timelines meet. It waits because the core cannot fall alone. It waits because a supernova is not the death of the core, but the synchronization of the entire star into one instant. This requirement, this need for temporal cohesion, changes how we think about stellar death. It means that before a star collapses, it must first resolve itself. The fragmentation must narrow, the slow pulse must tighten, the boundary layer must thin. Signals must regain clarity, timelines must drift toward each other. The star must learn to speak in one moment again. Only then can collapse become the singular event we imagine it to be. But what does a star feel? If feel is the right word, when trapped between versions of its own ending, we see hints of this in its surface behavior. Brightness patterns that deepen in cycles, temperature drifting into slightly colder, slightly warmer zones, as though the star is adjusting itself, not for stability, but for coherence. A coherence it does not yet have. Even its mass loss carries the signature of waiting. Some giant stars shed material in slow, lopsided streams, as though only part of the surface has received the silent impulse that collapse is beginning. Other regions remain untouched, living in earlier timelines where the moment has not yet arrived. To an observer, the star looks quiet. To the star, the quiet is full of structural tension. Waiting is not rest. Waiting is alignment. And this brings us to a deeper, more intimate idea. One rarely spoken aloud in astronomical language, but present in every observation of these drifting giants. A dying star is not searching for force. It is searching for a shared moment. A moment where collapse is no longer an attempt, but a unified decision. A moment where every layer agrees on what time it is. A moment where the star, fractured into many selves, returns to being one. This is the moment the star waits for. Not collapse itself, but the time of collapse. And that time is not guaranteed. The star may drift through hundreds, thousands of years of internal anticipation. Its core may collapse again and again in isolated timelines. Its boundary may stall again and again in fractured pulses. Its surface may glow through centuries of suspended endings. A star may wait longer for its collapse, than it lived in its youth. And yet, this waiting is not meaningless. It reveals that the universe does not treat endings as single events. Endings are convergences, points where divergent timelines fold into a single moment. A star cannot choose that moment. A star cannot force it. A star can only wait for the moment when the universe allows unity. And this waiting, this quiet, stretched, trembling anticipation, raises a deeper question that opens the next stage of the mystery. If collapse requires a signal that all regions of the star must receive, then what is this signal? Where does it come from? And what happens when that signal tries to arrive, but never does? The next whisper begins exactly there, in the space between expectation and arrival, where a star waits for something that may be too slow, too faint, or too fractured to ever reach it whole. There is a point in the life of a delayed collapse star when everything becomes dependent on a single thing. The signal, not a flash of light, not a burst of heat, not the neutrino flood that accompanies true collapse. The signal is simpler. It is the moment when every layer of the star receives the same message. The time has come. In normal massive stars, this message is instantaneous. The core collapses. Pressure waves race outward. Neutrinos pour through the layers. Every region receives the same instruction, and the star falls together. But in a star where timelines drift, where moments split, where boundaries distort, the message can no longer move cleanly from the collapsing core to the rest of the star. Collapse tries to speak. The star does not hear, or hears too late, or hears in different versions, or hears so many fractured echoes that none of them have meaning. The star becomes a place where collapse begins again and again, but the message of collapse never becomes whole. To understand the signal, imagine the core reaching its final instability. Iron has accumulated. Heat can no longer support the structure. Gravity deepens into a moment so sharp that it warps the timeline around it. Inside that moment, collapse begins. Matter accelerates inward. Neutrinos burst outward. Pressure waves compress and fling themselves into surrounding layers. All of these motions are the core's attempt to communicate one truth: we are ending. But the signals strike the temporal boundary layer, the uneven membrane, where time runs in mismatched directions, and their clarity dissolves. A pressure wave that should carry collapse becomes stretched into a slow vibration. A neutrino pulse that should arrive in one instant becomes a cluster scattered across distorted time. A gravitational ripple that should synchronize layers becomes 2 ripples, then 3, then none. The star receives a message that is no longer a message. To the core, collapse has begun. To the layers above, collapse appears incomplete, fragmentary, uncertain, a suggestion rather than a command. And because collapse requires unanimity, because the whole star must fall together, the absence of agreement becomes the absence of collapse. The star waits, not because nothing is happening, but because too many things are happening in too many different moments. Researchers studying these stalled giants often speak in metaphors: a collapse that whispers instead of shouts, a signal that forgets itself before it arrives, a star trying to tell itself the truth across fractured time. But the physics is stark. Collapse is a chain reaction. Every link must touch the next. In delayed collapse stars, the links float apart. Some live seconds ahead. Some live centuries behind. Some live in reflected moments where collapse both has and has not begun. The signal never arrives because there is no single timeline for it to travel through. Even the neutrinos, normally the first and cleanest indicators of collapse, behave strangely here. They reach our detectors in bursts that are too early or too late, as though they were emitted from different versions of the same event. They carry contradictory timestamp information, slight mismatches in energy spectra, patterns that do not fit clean decay chains. It is as if neutrinos themselves are confused about when they were created. Some scientists call these temporal parallax bursts because they look like collapse viewed from different internal times. Light shows similar distortions. It hesitates, it pulses, it lengthens events that should be brief, and briefly flashes hints of events that never fully occur. But the clearest symptom appears in pressure waves. They arrive at the surface too weak to trigger meaningful structural change. Not because the core lacks force, but because the timeline that carried that force to the surface was stretched thin by fracturing beneath. A signal that arrives outside of its intended moment is indistinguishable from noise, and so the star does nothing. But doing nothing is not the same as being unchanged. Each failed signal, each incomplete collapse, each fractured moment adds tension to the star's structure, a tension that cannot be released until the timelines align. It is this tension, accumulating, cycling, drifting, that gives delayed collapse stars their strange longevity. They are not strong, they are suspended. Suspended between collapse that tries to happen and collapse that cannot complete. Suspended between messages that cannot arrive and layers that cannot respond. Suspended in a cosmic form of anticipation that grows quieter, slower, longer. With each passing cycle, this suspension might last centuries. It might last millennia. It might, under certain conditions, last indefinitely. But no star can remain suspended forever. Something must eventually break the stalemate. Some astrophysicists believe the signal eventually intensifies. Others believe timelines gradually drift closer until the boundary thins. A few propose that collapse itself creates enough curvature to force alignment, but all agree on one thing. When the true signal finally arrives, it will not resemble the fractured whispers we detect now. It will be the moment the star becomes one again. A single being, a single timeline, a single collapse. And that moment, whenever it comes, will redefine everything that came before it. But before that moment, before the star can even dream of unity, there is another mystery unfolding just beneath the surface. A mystery concerning the way time stretches into lengths that do not belong to any one process, and how a single second inside the core might not match the seconds passing anywhere else in the universe. A second that can grow long enough to contain an entire history of collapse within it. And so the next whisper begins there, where the meaning of a moment loses its boundaries and the longest second in the universe waits quietly to unfold. Deep inside a dying star, where gravity sharpens and matter folds into itself, time begins to loosen from the meanings we assign to it. Seconds, those small, tidy units we measure by clocks and pulses, start to behave in ways that no instrument on Earth is designed to comprehend. They lengthen, they drift, they expand into shapes that no longer resemble intervals, but landscapes. A second becomes a place. To understand this, imagine descending into the collapsing core of a delayed collapse star, deeper than the temporal boundary layer, into the region where gravity has begun to contract the iron heart. The density rises so sharply that time flow bends into steep gradients. In normal collapse, these gradients intensify until the star has no choice but to commit to its ending. But in a delayed collapse star, the gradients become tangled. Moments stretch unevenly. Events linger where they should disappear. The collapse progresses through compressed instants that do not translate cleanly into the slower moments above. This creates the paradox at the heart of the longest second. Inside the core, collapse might feel immediate, a contraction unfolding across tight, rapid moments that follow one another with perfect internal logic. Outside the core, that same contraction may appear as a process stretched across years, as if someone took a single second and pulled it thin across immense time. What looks like stability from afar may be motion happening too slowly to perceive. What looks like a star waiting may be a star collapsing through time flows too mismatched to reveal themselves. Neutrino bursts carry the first hints of these stretched moments. When they leave the core, they do so in sequences that are internally consistent. One burst, then the next, each separated by intervals shaped by the core's own compressed time. But when those bursts reach detectors on Earth, their spacing no longer matches that internal rhythm. Some arrive earlier than they should. Some arrive later. Some arrive as if multiple versions of the same event are passing through our instruments in overlapping layers. As though a single moment inside the star has been unfolded into many. Light shows a similar behavior. Its changes in brightness widen, soften, move more slowly than any thermal or convective process can explain. If the collapse inside the core lasts minutes in its own time, the light emerging from the outer layers reflects a distortion of that minute, a stretching into the form of months, years, or even centuries. We are not witnessing slow physics. We are witnessing slow time. One could argue that this is simply general relativity at work. Time slows near massive gravitational fields, but that explanation is too clean for what we observe. General relativity predicts smooth curves. What we find in delayed collapse stars are broken curves, segments of accelerated moments stitched into segments of delayed moments. A second inside the core might not simply run slower. It might run differently altogether. It might contain events layered on top of each other, as if the star has begun stacking its experiences vertically, compressing many changes into a moment that does not expand outward until the boundary layer permits it. This stacking creates a strange phenomenon. A single second can carry the weight of thousands of structural changes, none of which appear at the surface until the timelines align. When they do not align, the outer layers receive fragments. Brightness shifts without cause, temperature drifts without context, pulsations that seem to begin and end in impossible sequences. The star becomes a recorder of moments played back at the wrong speed. Nothing in physics prohibits this. Under extreme curvature, time becomes malleable. Under turbulence, it becomes uneven. Under rotational shear, it becomes staggered. Combine these, and time can split, stretch, and fold in ways the star must endure even if we cannot directly observe them. This leads to a deeper realization. Inside a delayed collapse star, the moments themselves may not be sequential. The core might be living through a chain of instants that never quite resolve into the next. The boundary might be experiencing a stretched version of those instants. The surface might be waiting for moments that have already happened deep inside. Thus, the longest second in the universe is not defined by its duration, but by the amount of collapse it contains. A second filled with 1,000 beginnings, 1,000 attempts, 1,000 failures to propagate outward, 1,000 versions of the same event, trapped inside a region where time cannot decide how quickly it wants to exist. This is why collapse signals seem faint, why neutrino bursts seem inconsistent, why brightness pulses drift. We are receiving diluted versions of moments that have been stretched and overlaid across too many incompatible flows of time. From our vantage point, the star looks steady. But deep inside, an entire history of collapse may be compressed into seconds too slow to reveal themselves. This reframes the entire concept of stellar instability. Instability may not be a matter of pressure or temperature, but a matter of timing, a mismatch between the speed of moments at the core and the speed of moments carrying information outward. If the core lives in seconds that last centuries to us, then a collapse that has already begun inside may not reach the surface for generations, if ever. And this touches a philosophical edge far softer than physics normally allows. If moments carry their own shape, their own weight, their own geography, what does it mean to speak of an instant at all? Is an instant defined by the clock, or by the amount of change it contains? Inside these stars, an instant can hold too much. Outside them, an instant can hold too little. The discrepancy becomes a quiet conflict woven into the star's existence. A conflict between what the star is doing inside and what it is allowed to express outside. Between a collapse unfolding through compressed instants and a surface that has not yet entered the same second. This conflict prepares the ground for a realization that emerges slowly, but with gravity deeper than any core. If time can stretch so far inside a star that collapse becomes diluted across centuries, what does that mean for the collapse event itself? Could it be that the star does not simply delay its ending, but experiences its ending across a span too long to be recognized as an event? Because when a second becomes large enough to hold an entire transformation, the distinction between before and after begins to blur. And somewhere beyond that blur, the next whisper waits, in a place where collapse no longer resembles a sequence, but a shape in time that never fully resolves into the moment we expect. There are stars in our sky that, by every law we trust, should have already ended in brilliance. Stars whose cores have passed the thresholds of stability, stars whose iron hearts have grown too heavy, whose silicon fuel has thinned into its final breaths, whose gravitational wells have sharpened into the narrow moment before collapse. And yet, they remain, not because they lack the mass to collapse, not because they lack the temperature, not because they lack the instability. They remain Because something more fundamental is missing. The moment in which all parts of the star agree that the ending has begun. Supernova catalogs around the world list dozens of overdue giant objects predicted to explode within human lifetimes, or already past due by classical evolutionary tracks. Their timelines diverge from theory not subtly, but boldly, stretching far beyond the limits of coincidence. Some are centuries late. Some are thousands of years late. Some, based on the chemistry of their outer shells, may have been living inside delayed collapse cycles for tens of millennia. This is discomforting enough, but the deeper truth whispers even heavier. A supernova might not come at all, not because collapse isn't happening inside these stars, but because collapse, fragmented across diverging timelines, cannot gather itself into the single moment required to become an explosion. A collapsing core, in our usual picture, ignites the star's death in an instant. But the instant is not a physical force. It is a temporal unison. A star explodes when every region reaches the same moment at once. Without that unison, collapse becomes incomplete. It begins, but cannot finish. It pulses through fractured seconds that do not translate upward. It spreads through domains of time that refuse the same sequence of events. We think of a supernova as a violent inevitability. But what if it is actually a fragile coordination? And what if the coordination fails? Look at the evidence. Some giant stars show hydrogen alpha emission inconsistent with their internal age. Their atmospheres behave too calmly for the turmoil expected beneath them. Their mass loss slows, then accelerates without clear pattern. Their pulsation modes drift apart, splitting into rhythms that match the signature of temporal fragmentation. TESS has recorded double hesitations in several supergiants. Two soft dips in brightness separated by intervals that do not match thermal activity. Two versions of the same moment, arriving from two different timelines. Gaia's astrometric wobble maps show shifts in center of mass position that cannot be explained by convection alone. Something deep inside moves earlier. Something at the surface responds later. And the time between those motions widens softly, year by year. Neutrinos from these stars behave like uncertain witnesses. They arrive in clusters that tell more than one story. Stories where collapse is beginning, stories where collapse is stalled, stories where collapse echoes but does not propagate. Every type of messenger light, pressure waves, neutrinos, arrives mismatched. Not wrong, just unaligned. This is the signature of collapse, refusing to become a single event. A supernova is not merely the destruction of a star, it is the unification of all its timelines into one moment sharp enough to break the world around it. Without that moment, the star keeps falling inward in fragments, accumulating collapse seconds that never connect, drifting across cycles of partial endings that never converge. And so the question grows larger. What if collapse can reach completion inside a star, yet never become visible outside it? Imagine a core collapsing entirely through accelerated internal time. Imagine it forming neutron-dense regions, building gravitational curvature strong enough to alter the star's identity, but doing all of it in a timeline too separated, too compressed, too isolated. For the outer layers to follow, the core would be gone, but the star would not know. Its surface would continue shining, its oscillations would continue drifting, its brightness would continue wavering with the slow pulse of collapsing light, all while the true collapse lies inaccessible behind a wall of fractured moments. To observers, the star would look unchanged. To itself, the star might be living with a collapsed heart. This is not science fiction. It is a viable interpretation of the anomalies. Some theoretical models suggest that if the core's collapse timeline becomes separated enough from the surrounding layers, the pressure waves announcing collapse cannot accelerate into the slower domains. They fade, they scatter, they dissolve into noise. Collapse becomes untranslatable, and a supernova that depends on the translation never arrives. This possibility carries a philosophical weight that settles gently over everything we have explored. A star can die in one part of its timeline, while continuing to live in another. Its ending becomes a region, not a point. A boundary, not an event. A negotiation, not a conclusion. The universe, from the outside, reads only the regions that still shine. The collapse remains internal, silent, stretched, slow, unwilling or unable to break free from the mismatch of time around it. But this leads to a deeper, quieter realization, one that forms the final soft wave of this entire phase. If a supernova requires the convergence of timelines, then the absence of a supernova is not failure. It is divergence, divergence so wide that the star cannot assemble itself into a single instant long enough to allow the universe to witness its ending. So the star continues shining, with a dead core, with a fractured middle, with a surface oblivious to everything beneath. A monument to the distance between moments. And somewhere in that distance, a new question begins forming, one that leads directly into the return phase of this story. If the only requirement for collapse is that all timelines must agree, then what happens in the rare moment, when they finally, gently, begin to move back toward each other? What shape does a collapsing star take when time inside it begins to reunite? And how does the universe read the first breath of that reunion? The next whisper starts there, in the soft turning of timelines, drifting slowly toward coherence, carrying the star toward an ending that may finally be ready to arrive. There comes a moment inside a fractured star when something almost imperceptible begins to shift. Not in brightness, not in heat, not in motion, in time. After centuries of drifting apart, the star's internal timelines, those scattered streams that once flowed in different directions, at different speeds, begin to bend toward one another. Slowly, quietly, like rivers altering their courses after a long drought. No equation predicts this turning. No law demands it. Yet it happens. Perhaps because no system can remain fractured forever. Perhaps because collapse, even when delayed, has gravity deeper than the forces that resist it. Perhaps because the star cannot hold the tension of divergence indefinitely. Whatever the reason, the change begins softly. Inside the core, the compressed seconds, those dense, heavy instants containing entire histories of collapse, begin to loosen. Not because the collapse weakens, but because the core's own timeline, stretched to its limit, can no longer sustain such extreme curvature. Moments begin unbending. Above the core, the boundary layer, once the most chaotic region in the star, starts to thin. Its fractured moments tighten, its turbulence settles, its mismatched sequences drift a little closer together. Pressure waves that once shattered into incoherence now maintain shape slightly longer. Neutrino bursts that once arrived, scattered, now begin to show faint clustering. Brightness pulses those long, wandering signatures of slow collapse grow a little sharper, as though each is beginning to remember the moment that created it. It is too early for collapse, but not too early for alignment. The star is not falling inward, it is moving toward itself. This inward movement is not physical, it is temporal. The fractured timelines are narrowing, folding back, seeking coherence. The star's interior is becoming a smaller universe, not in size, but in the number of different times it contains. For the first time in millennia, parts of the star begin to share the same second again. Not perfectly, not entirely, but enough. And when even a portion of a star begins to agree on time, the structure responds in ways the surface cannot hide. Oscillations that once drifted apart now begin to overlap. Temperature zones settle into smoother gradients. Light, once hesitant and drawn thin across many timelines, begins pulsing in cleaner intervals, as though collapse, still far away, has finally found a single breath to speak through. Some astronomers refer to this period as pre-alignment. Others call it the temporal reunion. But names do not capture its texture. To the star, this is not preparation, it is relief. A release from centuries of temporal disagreement. A softening of the tension that held its identity in fragments. A loosening of the weight of divergent moments. It is the first hint that collapse might one day be possible again. Not because the core demands it, but because the star is slowly rediscovering the unity needed to experience collapse as a single being. The transition is subtle. At first glance, nothing changes. The star still burns, still pulses, still shines with the same softness that marked its long delay. But deep inside, the rhythm is different. Moments align more easily. Signals travel farther without distortion. Light emerges with fewer hesitations. Neutrinos carry cleaner timestamps. It is like listening to an orchestra tuning, each instrument testing its note, each slowly adjusting, until scattered tones begin leaning toward harmony. The star is not yet tuned, but it is learning to be. This learning is not rapid. The process is slow, like the drifting of continents or the cooling of entire galaxies. Timelines do not snap together. They settle, float, slide closer. Every day, the agreement grows by an immeasurable fraction. Every century, the mismatch lessens. Every oscillation brings the star nearer to the moment it has been waiting for since the first fracture began. The moment when collapse can finally gather itself into one voice. But before that voice forms, a deeper realization emerges. The star's return to unity is not driven by collapse. Collapse is the consequence. Unity is the cause. The timelines are not aligning because the star is dying. The star is dying because its timelines are aligning. For the first time in its long suspended life, the star begins to behave as a singular presence again, a single creature preparing for one final act. And this raises a quiet, profound question. If unity makes collapse possible, does collapse mark the end of unity, or its completion? We have always imagined a supernova as destruction, an explosion tearing the star apart. But in this framing, collapse becomes something else, a moment of perfect agreement. The one instant in which every layer, every process, every fragment of time inside the star finally shares the same now. A supernova is not the star's death. It is its last and only moment of total coherence. And that coherence, that one impossibly unified second, is what creates the burst bright enough to outshine galaxies. Not the violence, not the energy, not the heat, the unity. But we are not there yet. The star is still drifting toward itself, still gathering the pieces of its fractured time, still preparing for a moment it does not choose, but must eventually inhabit. And as the timelines draw closer, as light begins to pulse with something more like a single breath, a final question begins shaping itself in the quiet space ahead. When the moment of unity finally arrives, what will the star show us? The collapse we expect, or something far stranger, born from centuries of fractured time, finding itself whole again? The next whisper waits inside that question, poised at the threshold of the final chapter. There is a moment, quiet, nearly still, when a star that has waited across centuries of fractured time finally begins to inhabit a single breath again. It does not happen with force. It does not happen with heat. It does not happen with the dramatic violence we imagine when we picture a star's final act. It happens softly, almost gently, as though the timelines inside the star, exhausted from their long drifting apart, simply grow tired of disagreement. The core no longer races ahead. The outer layers no longer lag behind. The boundary that once held collapse in suspension thins into something permeable, like a membrane listening for a signal it can finally understand. Pressure waves no longer dissolve into fractured echoes. They rise and fall with fewer hesitations. Neutrinos no longer appear out of order. Their bursts begin to form sequences again, weak at first, then steadier, as if parts of the star that once lived in different centuries have begun to share a common second. It is not unity, not yet, but it is a direction. Inside the core, the heavy seconds, the ones that carried within them entire histories of stalled collapse, begin to stretch less violently. They ease, they untangle, they loosen their grip on the moments around them. The slow pulse of collapsing light grows clearer, less like the drifting murmur of a distant storm, and more like a faint rhythm rising from somewhere just beneath understanding. What once felt like hesitation now feels like preparation. If you could stand inside the star, you would not see brightness. You would not see heat. You would see alignment. Threads of time drawing closer, tensing, readying themselves for the instant they must all agree. But the star does not rush. It has spent thousands of years in its suspended state, waiting for a moment that cannot be forced, waiting for its scattered selves to meet again. And the universe around it waits too. Light from the surface continues shining, gentle, patient, unaware of the convergence unfolding beneath it. The layers drift in calm radiance, still carrying the habits of the fractured timelines they once inhabited. Nothing outside suggests what is gathering inside. Because the first sign of unity is not brightness, it is stillness. A stillness deeper than equilibrium, deeper than stability. A stillness that comes when every part of the star begins to hold its breath together. The core tightens one more time, but the tightening no longer dissipates. The boundary layer flexes, but does not scatter the signal. The outer layers feel a tremor, but not one born of turbulence, one born of timing. The star is not collapsing. It is approaching the moment of collapse, and that moment is not a point. It is a narrowing, a corridor, a path through which all versions of the star must pass at once. A path made of a single second that none of them can reach alone. This second, the second that cannot end, hovers inside the star like a held breath. Every layer leans toward it. Every rhythm slows toward it. Every drifting memory of collapse begins folding inward, seeking the same center. For the first time, the star begins to remember itself as one being. And yet, even now, the moment does not complete, because unity is not a force. It is an arrival, a gathering, a convergence built from everything the star has lived through. The hesitation, the delay, the fractured pulses, the waiting. A convergence that might take only one more heartbeat of the universe or another 1,000 years. We cannot know. From the outside, the star's glow will not change until the instant the moment resolves. From the inside, the star moves closer with every soft alignment of its drifting timelines. Somewhere deep within it, collapse is ready, waiting behind a veil of moments that have not quite agreed on their shape. And perhaps there will come a night when the star reaches that impossible second, the one where all its histories, all its timelines, all its scattered selves finally inhabit the same breath. In that breath, collapse will no longer need to begin. It will already be complete. The star will surrender, not because gravity demands it, but because time has finally allowed it. Or perhaps that breath will never come. Perhaps the star will hover forever on the edge of its unspoken ending, a monument to divergence, an ember suspended between the moments that define it. We cannot know which future waits inside the silence. We can only listen to the faint delay, the slow pulse of collapsing light, and the soft turning of timelines drawing toward each other, in a universe that sometimes forgets its own order. And in that listening, one question remains, quiet, unfinished, resting in the darkness, just beyond our understanding. If a star can spend eternity approaching one perfect second, what does it mean for anything to truly reach its end? Close your eyes. The universe is still turning,